Thank you. And thank you both for this introduction and for this 3-hour introduction that he gave to this topic this morning. The purpose of my 3-hour talk here would be to talk more about the signal processing side, more into detail, not in the sense that I would like you to be able to understand or grasp every single detail, but try to look into how we do a number of things like the uplink detection, downlink pre-coding, why we select them in particular ways, and show you some of the expressions that we get in more general cases, in particular covering spatial channel correlation. And we have a blog called the Massive MIMO blog, this address, and in that one I actually wrote about spatial correlation a few days ago. So if you're interested, here I've tried to describe these topics in some more simple terms in general. Let's see if I can get my slides up here. So I call this presentation Advanced Signal Processing for Massive MIMO. And the topics that I will talk about today, I will give you a short recap of what Massive MIMO is. And then I will talk in particular about correlated Rayleigh fading and what that is, and provide you an example of how you compute the correlation, spatial correlation in the communication system. And then this correlated fading will go through all of the things we're going to talk about today. So one of them is the channel estimation, including pilot contamination. One of them is the uplink spectral efficiency. If we have time, I will go through in detail the downlink. I will talk something about asymptotic analysis when you have many antennas, what happens with different types of processing schemes. And then at the end, I will talk about what I call spatial resource allocation, trying to differentiate that from the classical type of resource allocation time and frequency that has been going on for a long time. Slightly short thing about power allocation, and finish up with a case study and some open problems. And as Eric was indicating, see if the pointer works. Yeah. This is based on an upcoming book that I've written together with my colleagues Jacob Hoydis and Luca Sanguinetti, which is currently under review for something called a Foundation and Trends in Signal Processing. And it's a monograph, 450 pages, so it's twice the size of the red book that Eric was giving commercial about this morning. And it's intended for PhD students, first year or so, that would like to learn this topic. Hopefully it will be appearing in the fall, and there will be printed books available for purchase, but the intention here also that you will be able to download this material for free as well, along with simulation code and everything. These slides will, by the way, be made available for you as well. So we will start creating some kind of repository for that, sending out some link hopefully in the evening today, and that will include more of the talks here as well. Let's see if So let's start with introduction. So when I talk about Massive MIMO here, I will only focus on the multicellular system, where we have a number of base stations represented by these arrays here. And we have a number of I call them user equipments, or UEs, in the LTE fashion. And we talk about the uplink and downlink communication, downlink from the base station to the users, uplink from the users to the base stations. And trying to define what is a Massive MIMO system. The canonical Massive MIMO system here is a multi-carrier cellular network with L, number of cells, that's a letter that will reappear many times. And it operates in synchronous TDD protocol, which synchronous means that the uplink and downlink transmissions in different cells are synchronized. So it's the uplinks that are interfering with each other and the downlinks interfering with each other. And this is something that you at least can achieve in practice within the neighboring cells, which is the important thing. The base station, number J, is equipped with a number of antennas, MJ, so it could be different for different base stations. And typically, in order to call it the Massive MIMO system, we have a large number of antennas. And exactly how many you have, that depends a lot on how you would like to define things. Maybe 50 or 100 is what you should expect in order to have a Massive MIMO system. Maybe 64 will be what they actually call Massive MIMO in an LTE system, for example. The base station communicates with a number of users in each cell. And this user in cell J is denoted as KJ. So you see this is the same kind of letters as in the previous presentation, but now I put subscript here to indicate that it could be a different number of antennas, a different number of users in each of the cells. And they are transmitting to these users. They are single antenna users, and they are all sharing the same time and frequency resources. And we typically have more antennas than users. Exactly how many more antennas, that depends a lot on how you would like to design the system. And we will look briefly on that later on as well. And each base station operates individually, so there is no joint data transmission from different base stations. They might coordinate things on the long term, like power allocation and things like that, in the same way as Eric was describing, but not in the short term. And they're operating using transmit precoding, that is linear, in the way that we have talked about earlier today, and also linear receive combining as well. So that is how I would define a massive MIMO system. And we saw a similar kind of figure earlier today, where we are taking the time frequency resources and chop it up into some kind of coherent intervals, so I prefer to call them coherence blocks, because they're spanning two different dimensions here. Spans the time dimension, and we have the coherence time, TC, and it spans the frequency dimension, where we have the coherence bandwidth, BC. And depending on what kind of multi-carrier modulation scheme you're using, you might have multiple subcarriers within one of these coherence blocks. And each of these ones, we are dividing them up in this following form. In the uplink, we send data, and out of this number of samples, tau c being equal to BC times TC, so that's the product of the time and coherence bandwidth. These samples are divided into tau u being used for uplink data, tau d being used for downlink data, and then we can have some pilots. And in general, these are tau p in number, such that tau u, tau d plus tau p equals the total number of samples that we have. And today I will focus, just as Eric, on having pilots only in the uplink, but you can potentially have pilots in the downlink as well. In terms of numbering, we have L cells, and we also then have L base station, because there's one base station per cell. We number them from 1 to L. There are KLUs in cell L. These are numbered from 1 to KL. And if you look at the intersection here between two different cells, I denote these channels in the following way. H. I use H as channels, and not G, as Eric was having earlier today. Then as a superscript, I say the base station cell number. So that is one of these 1 to L. In the subscript, I'm identifying where the user is. And first I write the user's cell number. In this case, the user is in cell L. So then it will be an L here. Then the user is called a certain number between 1 and KL. And that is number K in this, lowercase k in this case. And then we will have H, L, K, and then when I looked at the channel to, for example, base station J, I put J here in the superscript. So this is an example of the channel between the user K in cell L and base station J in another cell. And by switching the different indices here in the superscript, we can go through the channel from this user to any other base station in the entire network. And what's important to notice is that the length of this vector here depends on who is actually the base station. So in this case, when I'm base station J, it is an mj times 1 vector, or matrix. So this is the basic notation that I'm going to be using. And how do we now model these kind of vectors, these channels? And then there is the important thing of what is called correlated or spatial channel correlation. And had the following definition: a fading channel, H, is spatially uncorrelated if the channel gain, which can be written as the squared norm of the channel vector. So we just take each element, the absolute value square of it, and sum them up. That is then the channel gain. If we compare that one and the channel direction, which is just take the vector direction and see, we normalize it, so it's a rank, it's the length 1 vector. If these two things, the channel gain and channel direction, are independent random variables, then, and also the channel direction can take any direction. So it's anything being on like a unit sphere, in this case in some kind of complex m-dimensional space. But anyway, it's any directions, if all of them are equally distributed, equally likely, then we say that the channel is spatially uncorrelated. Otherwise, the channel is spatially correlated. And the point here is that it's very detailed requirements that you need in order for this to actually be an uncorrelated vector. That means that if you should have an example of something uncorrelated, there is one good example, the uncorrelated or IID Rayleigh fading that Eric talked about this morning, where the channel is complex Gaussian, has zero mean and an identity matrix as the covariance matrix, or we can also call it the correlation matrix because you have zero mean. And in this case, all the eigenvalues of this correlation matrix here are the same. It's an identity matrix, all of them are definitely the same. But that's one of the things where you can look at in order to see that something is spatially uncorrelated. You can probably come up with some other example where you have the same main properties, zero mean, and a correlation matrix being identity, and maybe something that's non-Gaussian. But apart from that, this is what the cases where you get uncorrelated fading. Yes.
In a real environment, don't you have like a partly spatially correlated channel? In some direction they are correlated, and in some direction they are not.
Yeah, absolutely. So in general, if we can say that any model where we have some kind of eigenvalue variations in the correlation matrix will have some kind of spatial directivity. So in certain directions, it will be more likely that the channels are pointing at. In some other directions, it is less likely. And that could, for example, be that you have two different levels. Some of them eigenvalues have the same value, some others are much smaller. There are any type of shape there on the eigenvalues would give you some kind of spatial correlation. And when can we say the spatial correlation is strong? Well, then that is the larger eigenvalue variations you have. And that you can measure in a number of different ways. You can, of course, compare the largest and smallest eigenvalue. But you can also look at how they look like and try to give some kind of evaluation. Is this a strongly or weakly correlated? Is they close to the same, or is it large variations? So it's hard to define something in exact detail.
Do we need to have independent or uncorrelated between the norm and the direction?
Well, they will. You can potentially have something that's uncorrelated there as well, I guess. It's not necessarily that they become independent. In this case, they become independent. But the important thing there is that there is a coupling. If you have a certain direction, then the strength of the channel will also not depend on which direction that you actually have a channel. So one key example here is what you can call correlated Rayleigh fading, where the channel H here is complex Gaussian distributed, have zero mean, and some matrix R as correlation matrix or covariance matrix. These are the same thing when you have zero mean channel. And as I said, the larger eigenvalues variations are in R, the more correlation we have in some sense. And based on this, I'm now defining the correlated Rayleigh fading that I will use during the entire presentation today. So we say that this channel that we looked at from user K in cell L to some other base station J is distributed like this. It has a zero mean, and it has a covariance matrix. And we see that the subscript and superscript are exactly the same here, so I'm only changing H to R, and R is then always used as a spatial channel covariance or correlation matrix. And in every coherence block, we get a new realization that is independent from the previous one. That is the block fading assumptions that we had previous today as well. The variations in H is described as some kind of microscopic effects when you're moving around a little bit in the environment and you're moving a few wavelengths or something like that. That doesn't change the big macroscopic changes that are described by this covariance matrix. This covariance matrix is, by the way, assumed to be known at the receiving base station, so the base station that are at the top here. And estimating something like that could be challenging. That's a research topic by itself. I'm not going to cover it today. You can essentially create sample covariance matrices and use that in order to estimate it. And see if the computer reacts. the eigenvalues and eigenvectors of this covariance matrix is describing the spatial channel correlation of the channel, which then means that the eigenvalues that are strong, their corresponding eigenvectors will say something about this is directions where the channel is more likely to point in. And maybe you have 5 very strong eigenvalues, and the corresponding eigenvectors will then hopefully, or with large probability, span the vectors. It will lie in that kind of subspace. And this covariance matrix, you typically generate it in some simulations using a model, and we'll discuss one example of that. There's a lot of effort being done into channel modeling in general, and how you can create models for these ones in a realistic environment. And the covariance matrix describes the macroscopic propagation effects. And one of those things is the average channel gain from an antenna at this base station that we're looking at to the user that we're looking at. And if you take the trace of a matrix, what is that? Well, that is to take either the sum of the eigenvalues or the sum of the diagonal elements. That's the same thing. And if you take that and divide with the number of antennas, then you get some kind of average of the value that you have along the diagonal. And that describes the average path loss from one antenna at the space station to this particular user. And this value, you can model it in some different ways. You can say that in decibel scale here, there is some distance, d, that describes the distance between the transmitter and the receiver. And then the path loss factor here, or large scale fading coefficient, will reduce, become smaller and smaller the larger the distance is. And the typical way of doing this in decibel scales is to take 10 times alpha, where alpha is called the path loss exponent, log 10 of the distance. And you can measure distance in different units. In this case, I measure it in kilometer, which means that if I put in 1 kilometer, well, then this term goes away, and it is only this factor here that describes the channel gain I will have at a reference distance of 1 kilometer. And that number can, for example, be minus 100 decibels, something like that, that you typically are going to lose over 1 kilometer distance. And in models of channels or this large scale fading, we usually also add a term here at the end that randomize things. It can be a Gaussian distributed, for example, and it's often called shadow fading. You often have zero mean and some kind of standard deviation that is describing how much channel fading you have. It might be 8 or 10 standard deviation, for example. And it's called shadow fading, and usually you view this as being that the probability that you're shadowed by big objects or something like that, which has some kind of practical meaning. What it really is that you take channel measurements and then you try to fit this into a model of this kind, and then you see that, okay, it didn't fit perfectly. But what if we add some random perturbation to this model and we put some Gaussian thing there? Now it fits much better, because now we get something that is also varying, is not following a straight line, a log distance figure. So by adding this thing and calling it shadow fading, you get something that at least slightly realistic. Yes?
In millimeter wave, the shadow fading could be blocking effects for communicating. How can we account for these effects here? Just by increasing the alpha, for instance?
First of all, I think in the millimeter wave, I think the line of sight is the most important cases there, where you would have a line of sight component in addition to this, now I've assumed zero mean, then it would have a mean value. But suppose that you have like one large reflection. It goes from transmitter to receiver, bouncing that wall. That's the only way of reaching me because everything else is blocked. Well, then this covariance matrix here would have a rank of 1 that describes that particular path. And then how much you lose on it, that path, that will be the corresponding eigenvalue that describes that. And typically this beta parameter here, this channel gain, changes quite slowly on time with respect to the channel fading that you get from coherence block to coherence block. So therefore we, in order to get some kind of capacity result, we always need to assume these things to be fixed. So people are fixed in a small world where they're moving around, getting new channel realization all the time, while this covariance matrices or this beta parameter that you can compute from it is fixed. And there are many other models than this that you can use in order to generate things. I have no intention today to claim that, or to give you any model that is a perfect description of reality. But I'm going to use this type of models with correlation in order to show you how the correlation enters the kind of expressions that Eric was describing previously today for the uncorrelated case, to give you some insights about what spatial correlation can do for us. So if you have a complex Gaussian distribution here with the covariance matrix R, how do you generate something like that? Well, you can, for example, create an eigenvalue decomposition where U would be the eigenvectors stacked in different columns, and D will be a diagonal matrix containing all of the positive non-zero eigenvalues. There could be some eigenvalues to the zero if you have a lower rank R than you have antennas M, for example. And in that case, this D only contains those eigenvalues, and this U here is not really a unitary matrix because it only has R columns. We can omit the eigenvectors that belongs to zero eigenvalues. Then a way to generate realization of the channels will be to take the square root of the covariance matrix and multiply it with something that is complex Gaussian with zero mean and have an identity matrix, so some kind of IID Rayleigh fading thing. What does it mean to take the square root of a matrix? Well, that essentially means to take this eigenvalue decomposition and take the square root of each of the eigenvalues instead. And in that case, when you have this Hermitian transpose of a matrix containing the eigenvectors, multiplying that with a complex Gaussian distributed variable with covariance matrix I, when you multiply like that, this thing here will just take away M minus R of the dimensions, where there is nothing here in U that spans it, and you will reduce the dimension of this thing here. So this U Hermitian E hat will be complex Gaussian as well, but with zero mean and identity matrix R of a smaller dimension. So essentially, in order to generate something like this, you just take a complex Gaussian distributed element with IID elements with the rank of your covariance matrix, multiply it, so scale it with the respective square root of the eigenvalues, and then multiply it with the eigenvectors, and then you have generated. So this is the way to do this if you would like to do it in MATLAB, for example. Yes?
What I have read about these models, that the independent model is more generally used in trying to simulate things and when we use a theoretical investigation. And these type of models are mostly used when we keep the practical constraint that antennas are very closely located with each other. So you haven't told us about the selection of how do we select a model, because in theory we always assume that they are all independent, and when we see the practical point of view, we should take the antenna correlations because of the close coupling.
Yes, so in theory a lot of people have been preferring to work with IID Rayleigh fading models, and the reason for that is you can get all these nice expressions that Eric was describing. Then there is probably no real scenario where you have exact uncorrelated fading. In some cases you might be close to it, in some cases you will be far from it. And the purpose today will be to show you what this correlation can have as an impact on the performance. And one of the answers I would like to answer, or question I would like to answer, is also, will you get better performance or worse performance by taking this correlation into account? Is all of this analysis that has been done with IID Rayleigh fading a conservative or an optimistic analysis of the systems?
So in this model, are pairs of H, are they uncorrelated?
Yes, so for different users, I assume that their realizations of the channels are independent. But they could have covariance matrices that looks very similar, and that is something that will play a part later on. A correlated Rayleigh fading vector with covariance matrix R has rank of R degrees of freedom. That is the size of the subspace which actually is living.
Are we going to make a difference between the correlation on the transmitter side and on the receiver side?
So in this presentation here, I'm focusing on having one antenna at the user side and multiple antennas at the base station side. So then you only need to model the covariance matrix for the base station. In the uplink, that affects the receiver. In the downlink, it affects the transmitter.
How do you generate the eigenvalues of R?
That we will come to in a moment. So you need to have some kind of model for covariance matrices, and in a real 3D PP system or a simulator of that, there is advanced models of how to generate these channel realizations. They're not even Gaussian distributed, but from those you can guess what the covariance matrix is going to be. I will give you one simple example that's used a lot in academia and that have some of the main properties. And then at the end, I will run a case study with real models from 3D PP. And the model that I'm going to introduce to you now is called the local scattering channel covariance model. The idea is that you have an array at the base station with uniformly linear array, for example. So the distance between the antennas is equally large. Then you have a user being located somewhere else, and there is no line of sight path between the base station and the user. And that gives the result that when I'm going to send my signal, it's going to bounce on a number of different objects here, and it will eventually find its way to the base station array, and we will get a number of different multipath components being received. And there is a main angle, nominal angle, to the user, and then there is some kind of spread of angles. So all of the different things that are coming in here comes in from slightly different angles around this nominal angle, which is what you're going to get on a map if you draw a line between them. See if my remote works. No. And I call a number of multipath components that are received by the base station by n path. And each of these paths reaches the base station from a particular angle. This is for the nth path, we call it like this, with the subscript n. And when you, to a uniform linear array, receive a signal coming from the far field with a particular angle, like this one, you have an array response that describes how the phase shift at the array is going to look like. And there are some standard expression for that. This is what you get from a uniform linear array, but for other types of array structure, you can get other things here. The important thing is that you get e to the power of 2j, something dh here that says what is the distance between the different antennas, and then something sinusoid here, for example, of the angle from which the signal is coming in. And we have normalized this so that we say that the phase is 1 at the first antenna. You don't necessarily need to have that. You can add an extra random phase on top of this one. It will make no difference in my derivation here. And the signal that is coming in from this direction have a particular random gain here, Gn. That is how much you have lost on the way. And this is now for one of the paths. So what we're really receiving is a superposition of these components for n, capital N path, different ones. And we would like to understand how to model something that looks like this, particularly when you get a lot of different multipath components. And let's now assume that the angles that is coming in is independent and identically distributed, and they have some kind of PDF here that says what is the distribution of the angles in the angular domain. Typically it will be around some kind of main angle, but it not necessarily need to be like that. It could also be uniform distributed. Then we have the gains. They are also assumed to be IAD distributed, have zero mean and some variance that I just write like that. And I now define the sum of these variances as beta. As you can expect, this is going to be the beta that was showing up before, the average path gain or path loss. And then from the multidimensional central limit theorem, when you have a lot of different paths, in probability, this channel will behave as if it's complex Gaussian distributed with zero mean and the covariance matrix R. How do we get this covariance matrix? We get it by taking the expected value of the received signal. So it's going to be a sum of the outer product between the array responses from each of the different paths here. And we have a lot of them. So this is holding in probability when you have a lot number of paths. If you now look at one of the elements, say row L, column M, and you expand this expression here, you will get a number of different things here. Since I assume that the angles and gains are independent, I get one expected value over the gains and one expected value over the part that contains the angles. And this part here, sum of the gains, was what I called beta. And this part here now, because I have identically distributed angles, I don't need to have a particular angle here. From path n, in general, I just can take away that subindex. I will get the same thing. And this expected value now can be written as a integral over my PDF of the angle distribution. And then this inner product here can be simplified in this form. And this is now a general way of computing a covariance matrix from a user to a base station. And it could be from any angle distribution that comes in. The only thing is that I'm assuming that we have ID angles and gains. If I now put in a particular distribution of the PDF here for the angles, I can compute this in the computer, or maybe in some case I can actually get an expression in closed form. So this is the expression that we have. And what is called the local scattering model here is not this general model, but actually when we assume that there is a lack of scattering around the base station. So all the multipath components are actually coming in from a small angular direction to me as a base station from the user. But, however, there is a lot of scattering around the user. So if this was the nominal angle between the user and the base station, all the multipath components here from the nth path will be equal to the nominal angle plus some random deviation around it. And in the literature, you can find a number of different distributions that people have been looking at in these cases. And this goes way back to the 90s, for example. People have been doing these kind of models when they started to talk about having multiple antennas at base stations. And one choice of the angles will be to have a normal distribution. Another will be to have a Laplace distribution. That's something that looks like a Gaussian distribution but have a slightly larger tails. You can also have a uniform distribution. Then you have a very strict, all the multipath components come in from this angle interval and nothing anywhere else. And in that particular case, this is often referred to as the one-ring model. I will choose the normal distribution, which I think is also the most common one in literature if you look back. And that's what I'm going to use in some simulations later today. In these cases, I have chosen this sigma here to be the standard deviation. So it's the same standard deviation in all these different cases. What happens now if I put this distribution into the integral expression and evaluate this numerically, all of the integrals, then I can create the covariance matrix. For example, in this case, having a user with or base station with 100 antennas, and the nominal angle to the user is pi over 3. I just took a number there, and I selected my angular standard deviation to 10 degrees. So that is the standard deviation of these variations where the multipath components comes into to me. And here I'm showing what happens with my eigenvalues of the covariance matrix of the user. And I've ordered them in decaying order. Here is a normalized eigenvalue. So in reference case here of uncorrelated fading, all the eigenvalues are 1, and therefore in decibel scale they will be 0. And with the different models here, the blue one being uniform distribution, there are some large eigenvalues here that almost tend to be larger than in uncorrelated fading case, and then it goes rapidly down. And some of the eigenvalues are very small, so not even shown here. Then with the Laplace and Gaussian distribution, it goes down a bit more slowly, but eventually you also get rid of all of the eigenvalues, and you have a number of eigenvalues that are almost 0. So we can say that in the uncorrelated fading case here, you have a 100-dimensional space where the channel can appear with high probability. With this uniform distributed, you have perhaps a 20-dimensional subspace of your 100 space where the channel is likely to be. And with this Laplace or Gaussian distribution, you have a slightly larger one, maybe 30, 40 size of this subspace where it actually lies. And there is a lack of channel measurement for massive MIMO systems, so we don't know exactly how this is going to look like in a real system. But we can expect that there are going to be some eigenvalue variations in those cases as well. And I will in particular work with the Gaussian distribution. I will change around this angular standard deviation as well in simulations, and sometimes I will compare this with the uncorrelated fading case.
What would happen for eigenvalue distribution if we have single clusters as well, not only local clusters?
So I would say that if you make this model more general, so that you don't only have like one cluster here around the user, but signal could bounce to another cluster and then come here, then that will add more and more components to this model here. And I think what that will, for example, lead to is that the reason that it goes down abruptly here is that this cluster is relatively fixed in the angles. So the number of eigenvalues that are non-zero here depends on how large this angle area is. If you add additional clusters around, they will also contribute and widen this area where you will have get in multipath components, and that will probably push down the top eigenvalues here, push up the lowest ones, and you will have something that goes down more slowly and more slowly. One simple example of what could happen if we have a lot of spatial correlation in the system. Now I'm just for a moment looking at the single cell system with k users, and the received signal y is a sum of signals sent from each of the users. Si denotes the signal from user I. Here's the channel, and then we add some noise here to it as well. And we're using this correlated Rayleigh fading model for all of the channels. In particular, I'm assuming that the covariance matrix to user k have this form here. I take a covariance, I take a unitary matrix U here, but I cut away a lot of the eigenvalues or eigenvectors here. So I assume that I have only m over k eigendirections where the channel exists, and then the rest of them are 0. And within that eigenspace, I have like an identity matrix here in the middle with my eigenvalues. So I have like two values. Constant eigenvalue, 0 eigenvalue. And in order to make sure that the trace is always the same here, for example, equal to m, I need to scale with k. So these eigenvalues that are non-zero are k, the other ones are 0. Now we'll look at two different cases. The first case is when the users have orthogonal covariance matrices, meaning that if I take this U matrix from a user, multiply it with its own U matrix, I get an identity matrix. If I take different ones for different users, I get 0. That is because they are having different eigenvectors. They are spanning completely different subspaces. So their channel will live in different subspaces. And this is how we can generate something like that. The other case is when these U matrices are the same for every user. Their channels are now lying also in an m over k dimensional subspace, but they have the same values. So uk is the same for all users. So when I multiply uk with ui from another user, I will get identity matrix all the time because they're the same. If I now, when I receive my signal Y and are interested in the signal from user K, multiply with this G matrix from this particular user, then I multiply this with each of the user's channels. And if I expand HI, as I had on the previous slide, as UI, some vector EI that was uncorrelated Rayleigh fading in the signal here, then I get this inner product here between the different U matrices from user K and user I. And in the first case, where these two were either an identity matrix when it was the same user, or 0 when they're different users, well, all the terms in this sum goes away except the one that comes from the user of interest. So the received signal here is only containing the signal of the user of interest plus some noise. But it's also Gaussian distributed. In the case where the U's are always the same, well, nothing happens except that we replace it with an identity matrix. So we still have a sum over different user signals so they interfere with each other. So what we see here is that the spatial channel correlation can be very beneficial if the users have different eigenspaces. If they have very different covariance matrices. Then we separate here so each user is like operating orthogonal to the other ones, like in a single user system. However, when they have the same space, well, then they are interfering a lot with each other, and they are not even getting all of the M antennas. They are living in M over K antenna world. So this will be a first observation of how spatial correlation could affect our system. Let's now define the uplink transmission system model that I'm going to use today. The received signal at base station J is a sum over signals transmitted by all the users in the entire system. Some of these users are within my cell, and therefore their signals are desired. So here is the sum over all the users in my own cell, the 1 to kj users. There's their channel and their signal sjk. Their signal have some power, p lk or pjk. You just take S0 and replace it with p, then you get the power of that signal. And if it's a random data signal, well, then I will assume that this data signal comes from a Gaussian codebook, having this p lk as the power. And if it's a deterministic pilot signal that we're going to send later on, well, then it's just having this as absolute value square. Then I receive signals coming from other cells, all the other cells, all of their users summed up here, the channels from user I in cell L to my base station J, and their signal that that user is sending. And then at the end I'm adding noise here at the side. So this is the model of a multi-cell system with this notation that I've described. And the receiver noise have identity matrix as covariance matrix times some sigma square. And in these cases I have not put the variance of the channel to 0 or to 1, but I keep it here, particularly because the book that I have written is dealing with energy efficiency in addition to spectral efficiency, and then it's very important to separate how you get an SNR. Is it because you have a large amount of power, or is it because you have a low path gain, or if you have a lot of noise variance? What we will do in the uplink, similar to what Eric was describing, is that we apply a linear receiver. And here I call this linear receive combining, where I, at my base station in cell J, would like to detect the signal from its kth user. I'm just selecting a vector, which I call the linear receive combining vector, or it can also be called the linear detection vector. It's an mj dimensional vector that I use to multiply or take an inner product with the received signal. That means that I take now the inner product with each of the different terms that I had in my uplink received signal model. Now, since I selected this receive combining vector for my kth user, I have one term here that contains the signal from that user. Then I have one term that contains the signal from all the other users that are within my cell. They are desired to me, but right now when I use this receive combining vector, I will like this to be small value. And then I have intercell interference as well. And then I have some noise. And we will look later today on how to select these combining vectors in a good way. We have seen maximum ratio as zero forcing as two options earlier today, and we will look into what will be the actual optimal thing and how you, from those ones, can interpret what zero forcing and maximum ratio is as well. And briefly, what is linear transmit precoding in the downlink? Well, in these cases, in the downlink, when the base station is sending signal to the users, I have a very similar system model. The received signal at user K in cell J is a scalar now because I only have one antenna. I'm using the same notation now for the channels, except that I put the Hermitian transpose. Actually, if it should be strict, it should be a real transpose here. There's no conjugate or something like that. But we take this Hermitian or conjugate transpose just to get the expressions to look nicer. You can always undo that complex conjugation in the real practical system. And what I get is this vector channel from the base station multiplied with something that is the precoding vector. So the signal that base station is sending is a sum. Base station L sends a sum over signals that are intended for different users. And we have a precoding vector which has a norm 1 that is pointing out the direction of that signal. And then we have this sigma Li that is describing the data signal. Also being compressed Gaussian codebook and have a power rho LK in this case. That means that the received signal then in the desired part contains my channel from my base station, my precoding vector, and my data signal. Then I have some intracell interference. So these are signals that are sent to the other users in the same cell, their precoding vector, their data signals, but my channel from my base station. And then I have the signals from all of the other cells. Here is the sum of the cells, here is the sum of their users, here is the channel from that base station to me, here is the precoding vector of each of the users and their data signals. And then at the end we have noise. So that is basically the model that we're going to use. So model for uplink, model for downlink. And do you have any questions at this point? Otherwise I will move on and start using this model for channel estimation. Let's move on. So in the uplink for channel estimation, remember that we describe the coherence block like this. I have uplink data, downlink data, then I have uplink and downlink pilots. And we will only focus on the uplink pilots part. And this total cake of pilots, tau p, is divided by tau p u for uplink, tau p d for downlink in case you use that one. So tau p u is what I'm going to use for the uplink case here. And what I'm sending as a base user is so-called pilot sequence. This pilot sequence is a vector of length tau p u, so that's length of number of samples I'm using for uplink signals, and user k in cell j using a pilot sequence called psi jk. And the sequence is normalized such that if I take the square norm of it, it is equal to tau p u. And now when the user is sending the signal, it's just taking the signal or pilot sequence and multiply it with its uplink power, which was pjk. That means that as a base station, I'm receiving over my channel a sum over all my users. Here are the kth user in my cell's channel. Here is its pilot sequence, and here is the power that it is using. Similarly, from all the other cells, some of the cells, some of their interfering users, here are their channel to my base station in cell J. Here is their power, here is their pilot sequence. And here is a matrix now with noise, because this is what they receive during the entire pilot signaling. So it's a matrix, number of antennas times the length of the pilot sequences. But it still contains complex Gaussian distributed zero mean and sigma square uplink variance noise elements. What can I do now as a base station? Well, I would like to use these pilot sequences. These are something that is known to me, and I will use them to learn my channels to each of my users. Say that I'm focusing now on the kth user in my cell. Then the first step that the base station will do is to take this received matrix and multiply it with the sequence of the user of interest, psi jk. And this is the first step in order to learn this channel that I have from me as a base station to this user. And multiplied means that I'm correlated, or multiplied from the right here, so that I get the vector of dimension number of antennas. And what will it contain? Well, it will contain all of the same terms as before, but in each of the terms I have multiplied from the right with a pilot sequence. And then you see that all of the times here we get inner product between a pilot sequence of another user and of my use of interest here. And this is and first of all, the reason that I'm correlating with this thing here is that's something that comes from estimation theory. I'm essentially removing everything that is not coming in from the same direction as the pilot sequence of these different users. This is a called sufficient statistic for this, so that you don't lose anything from doing this. Yeah, in the back.
So even with a correlated channel, the channel hardening will apply there also?
That we will see later on. So far, this is done on a coherence block by block manner. So right now, H here have taken one random realization. Doesn't matter what kind of distribution it comes from.
So do we need downlink pilot estimation?
That depends on if you have hardening or not. And as Eric was describing, you don't necessarily need to have any pilot sequences in the downlink in order to learn the channels, even under imperfect channel hardening. The important thing is that you have a lot of antennas, or that you're sending a long block of data so you can use that to learn the channel anyway.
So in multi-carrier system, do you apply the same sequence for the subcarriers?
You can have the same sequence on all subcarriers for the reason that we assume that the statistics are the same in each of these coherence blocks.
Are you assuming that the whole network is synchronized? So you can
Yes, we have assumed that the whole system is synchronized. In practice, you can make sure that your cell and the neighboring cells are sufficiently synchronized. For example, in an OFDM system, all of the variations that are within the cyclic prefix, or the distance of that, which is like 2, 3, 4 kilometers, depending on which length of the cyclic prefix you're using, those will easily be synchronized. But further away, things will definitely never be synchronized perfectly. That is something that we assume here to keep the math simple. Let me now look at what will happen. And we see that the interfering terms here contains this inner product between the pilots of my desired user and other users in the system. Ideally, we would like to make sure that this inner product between two different users are always equal to 0. But in a large system, of course, we cannot do that, because if you would like to make two sequences of length tau pu orthogonal, well, you can only find a collection of tau pu different sequences of that kind that are like a basis, orthogonal basis for the subspace, and that are all mutually orthogonal. So there is only tau pu sequences that you can generate. And if you have more users than that in the entire network, that is a problem for you. What we can try to do is to say that my network have tau pu mutually orthogonal uplink sequences that we put as the columns in a so-called pilot book. I just use the name code book and call it pilot book. So the columns here are the pilot sequences. And that means that since they are orthogonal to each other, if I take this matrix and multiply it with itself, in this way we get an identity matrix. And it's scaled in this way because I assume that each pilot sequence have a square norm of tau pu. Now, if tau pu is greater or equal to the maximum of the number of users that I have in any of my cells, I can at least make sure that within each cell my users are using different pilot sequences. And I can create some kind of way, some manner, we will look briefly on that later, where some manner where I take my pilot sequences and assign them to different users. First, I design them within my cell so that they have different pilots, and then I can think about how to do this between cells. And Eric was describing some different pilot reuse patterns earlier today. We'll come back to that as well. In the general form, I can just say that there is a set of users that use the same pilot as me, and now I am user K in cell J still. And this set of users are those users I in cell L that are such that they're in the product between their pilot sequence and my pilot sequence is non-zero. And actually it will be equal to tau pu with this type of design. In this case, what will happen with the expression I had before? Well, a lot of terms in the system will be zero because a lot of users will use different pilot sequences than me. Who will not do it? Well, that will be a sum of users that use the same pilot sequence as me, and let's remove myself from it and put it over here, so that here I have my channel, my power, and then the inner product between my pilot sequence and my own ones, that is tau pu. And here I have the interfering terms, all the other users that are using the same pilot as me, their channel to my base station, their power, tau pu showing up again, and here I have the noise term. And the noise term is actually also changing its variance when I multiply like this. So it's at variance sigma squared times tau pu. So in this simplified expression, I now see here who is actually interfering with me in my pilot transmission. Well, that is all the users that use the same pilot sequences as me, but no one else in the system. I can now use this, put it into some classical expressions from estimation theory. And actually, the nice thing is that estimating Gaussian unknowns in Gaussian noise and interference is like the basic case in channel estimation. You can open up the book by Stephen Kay and see that this is one of the first things that are described there. And they're also covering cases where you have correlated unknown elements. So this is how the MMSE estimate is formed. You take your received signal Y that you received from data signals. And in this case, I'm actually not only looking at the channel from user K in cell J, but from any user in the entire network to my base station I. I take the received signal from the pilot transmission multiplied with the pilot sequence of this user. Then I multiply with the matrix, which is this matrix is essentially the inverse of the sum of the covariance matrices of the signals that I receive. So these are all the users that use the same pilots as this user I'm interested in. Here is the covariance matrix of their channel. Here is the power and the tau pu. And here is the sigma squared times the noise. So this is like the covariance matrix of Y that I receive here. And then I multiply with the covariance matrix of my user of interest and with the power, and then I have estimate. That is what basic estimation theory is telling us that we should do. And from this thing here, one can also compute what will be the estimation error. That is the true channel minus the estimate here. And this has a particular structure for each covariance matrix as well. It's the original covariance matrix of the thing of interest minus something. And this is looks a bit ugly due to all of these different indices here. What's important is that when we have established something like this, there is a nice way of generating estimation or estimates of the channel and estimation errors. We can just take the and say that the estimates of my channel here, since Y is a Gaussian thing and multiply with number of thing, it is still a complex Gaussian random variable with zero mean, and it has a covariance matrix that is the original one minus this estimation error covariance matrix. This is what for H, this is from the estimation error. And the estimation error, complex Gaussian, zero mean, and have this covariance matrix. And this estimation error, they are independent random variables. Well, that's something that comes from estimation theory. So this is how you can generate estimates and estimation errors. Some things to look at, say that we are just having one user in the system, and we are defining some kind of effective SNR being the transmit power times tau pu times my variance of the channel divided by the sigma square noise here. Then I'm plotting here what I call the normalized mean squared error. That is to take the trace of this estimation error divided by the trace of the original covariance matrix. Why do I divide with this? Well, now I get a number between 0 and 1. And by looking at something like this, you can compare the estimation quality to different users and say that when I have a perfect estimate, so the estimation error is 0, well then this normalized MSE is equal to 0. When I have a totally bad estimation procedure here, then the estimation error will be the same, have the same covariance matrix that the signal I have from the beginning, and then I will have a 1. So when I'm not plotting the estimation quality in terms of normalized mean square error, when I have a very low SNR, we will start up here at 10 to the power of 0, which is 1. And then as I'm increasing my SNR, the estimation quality will improve. It will go down here in normalized mean square error. And the interesting thing here, this is when I estimate with 1 antenna. This is when I estimate with 10 antennas. This is when I estimate with 100 antennas. How do I get better normalized mean square as I add more antennas? Well, this has to do with what model I'm using. I'm using this local scattering channel model with the Gaussian distribution of the angular spread, and they have a 10 degree angular standard deviation. And that means that the more antennas I have here, the more this fact that I am concentrating on some eigenvalues will make it easier for me to estimate the channels. In a case where I have an independent Rayleigh fading, as Eric was looking at today, the blue and red curve here will all coincide with the black curve. While when I have correlation, it becomes easier to estimate my channels. The curves are going down here. It's not like they're going to go down to 0 as I add more antennas, but it becomes simpler to estimate correlated channels because they have a structure. Because I essentially only have to estimate some of the eigen directions, and they are stronger, so I have better estimation performance here. This is one of the basic properties that comes from correlation. Easier to estimate the channels.
Is the matrix inverse?
Sorry?
So the matrix inverse you have to compute. Is that the size, the number of antennas?
Yes.
Can you do that? I mean, in practice?
That depends on how many antennas you have. But that is definitely one of the issues with the channel estimation itself, that in this expression you need to compute if you have 100 antennas, 100 by 100 matrix. There are research that have been done on how to approximate those things, and I'm not covering it today, but in our book we also have something that we call the element-wise MMC estimation, where we are estimating the channels one at a time with an MMC fashion, and then you are reducing the complexity because you estimate as if you were in a one antenna system, but you will lose in terms of performance. The blue and red will end up at the black one. So you can essentially say, and this is an important thing you bring up, that if we can afford the complexity, we can exploit this. If we can't afford the complexity, it will not be worse than in the IID Rayleigh fading case, because we can always estimate each element separately and not use the correlation between the elements. There was one question more?
Is this similar to the channel hardening effect when we go with M? When M tends to infinity, normally the channels tend to be orthogonal to each other.
No, this is actually not related to the channel hardening, but rather the opposite effect, that the channel is living in a smaller subspace, so that you only have a few eigenvalues. It's like you have, say, 100 antennas, but the thing you're trying to estimate is actually only 20-dimensional or 40-dimensional, because that is how many large eigenvalues you have. And that will mean that there's only 20 or 40 antennas that contribute to channel hardening, so you have a less hardening effect, but you have a better estimation quality because you only have to estimate something of smaller dimension, approximately.
Yeah, but the channels belonging to different users will become more orthogonal when we go, and even if we have the correlation amongst the attribute of one channel network belonging to one user, right?
So the interference that comes from different users is not covered here. I will talk about that in a few minutes. So let's save that question.
The position of users affect the performance. I mean, if users are close to each other.
Yes, let's save that question as well.
Will the anchorness or standard deviation increase? When that increase, will it become easier or harder?
So if you increase the standard deviation, you are decreasing the spread from where the signals are coming in. And so higher standard deviation means less spatial correlation. So as you increase this one, these curves will move up towards the black one, and eventually it will be very close to that one. And if you instead are decreasing this number, you get more correlation, you get fewer eigenvalues that are strong, and then these curves will move further down.
Well, I want to talk about the selection of MMSE estimation. As you told that these channels are correlated, so they must be dependent on each other somehow. So the recursive algorithm must perform well in this scenario.
Yeah, so I am not exploiting any information between coherence blocks here. But if you do that, I guess the better your estimates are here, the more prior information you have, the easier it will be to apply a Kalman filter or something like that. But I haven't looked into that myself in a correlated case. Another question?
Yeah, so what would happen if you let the number transfer to infinity here? Would it go to zero?
No, it will not go to zero as you add more antennas. It depends, of course, which channel model you have. But there could be channel model where it actually goes to zero. In that model that I'm using here, you're always going to have, say, 30% or 40% of your eigenvalues being strictly non-zero. So you will always have those ones to estimate. Let's move on. And
so if you have mobility, do you have to update your MMSE?
yeah, so everything here is assumed that the user is living in a small world here where it gets new channel realization but same covariance matrix. If in practice you need to somehow learn this covariance matrix and update it, there are some algorithms that people have imposed for these things. I don't think that is a mature topic yet, so I will list it later today on the open problems. But learning something about the spatial structure of users and in order to apply this to simplify things is one of the things that needs to be shown in practice if you actually can do it. Okay, so looks now at two users that use the same pilot. User K in cell J and user I in cell L. The indices here is not important. The important thing is that their pilot sequences are the same, and that means that the set of users that use the same pilot sequences as them is also the same. They are sharing the same pilot. If you look closely into this expression that I had, that would mean that this matrix with the inverse of the covariance matrix of the received pilot signal, because it will be the same, and that the received pilot signal when we are multiplied with my pilot sequence is the same because you have the same pilot sequence. Then one can say, okay, but the estimate of the channel from base station J to user I in cell L had this expression. Now I know that this psi matrix is the same for two users, so I can switch the indices. The received pilot matrix when I multiply with the pilot sequence is also the same, so I can switch here. And then let's assume that the covariance matrix of my own user is invertible, so I can put it in here. The covariance matrix times the inverse of it. Then I can now notice, but look, this part here, this is actually the estimate, the expression for the estimate of my own estimate, of my own user. H hat J subscript channel from base station J to kth user in cell J. So that means that I now have a relationship between the estimates to my own user and the user in another cell. The only thing I need to do is to take the inverse of a covariance matrix, multiply it with that one, so remove my own covariance matrix, then I multiply with the other user's covariance matrix, and then I rescale the powers that they're using, potentially using different powers, and then I get the other estimate. So what does it mean? It means that the estimates are correlated. If you have generated one of them, you can multiply it with the sequence of deterministic matrices and scalars, and you get the other estimate. So they are definitely correlated random variable. And that is one of the results of what we call pilot contamination, that they are interfering with each other. However, they are like rotated version of each other, because if you multiply with these matrices here, somehow you will take the estimate of one user and rotate it somewhere else in the vector space. In the special case where the covariance matrices here are scale identities in the way that Eric was looking at earlier today, well, then these two things here will just be in identity matrix times the inverse of identity matrix. That will not change anything. In that case, the estimate of the user in the other cell will be equal to the estimate of my own user times some scalars. Meaning that in that special case, these two channel estimates are exactly the same up to a scaling factor. In general, when one of the matrix times the inverse of the other matrix is not a scale identity, they are correlated vectors pointing in different directions. Yes?
The received signal are different cells.
Mm-hmm.
Cell G and cell L. Why are they working?
So which one?
Why are the Y, G, K, and
These ones. Okay, so these ones I defined one of them earlier here as you take the received pilot signal matrix here at the base station and multiply it with the pilot sequence of my own user. If this sequence is the same for the two users that I'm looking at, well then I get the same thing here even if I change the indices here. So I use Li here and Li here, they will still have the same value. But I didn't define that properly here on the slides. So look now at the first time of what we call pilot contamination effect, where we say that two different users are using the same pilots. Then the received signal at base station in cell J is the sum of the channels from two users. You have their powers, we have the tau pu, length of the pilot sequences, and we have some noise. And if you take these two estimates of the two channels that we just looked at, these were correlated with each other. So if we form a correlation matrix, we will see that they're zero. If we take the inner product between them and say divide with number of antennas, take the expected value, you will get some expression here that is zero when they are using different pilots and non-zero when they are the same. The exact expression here is not so important, but it's this curious thing that these two different channels are assumed to be independent random variables. So if you take the true channels and multiply them like this, the expected value of them is zero. But when you take the estimates, it's not zero, due to the fact that the base station is observing the sum of them when it estimates, when it's in the pilot signals. And this is what we call pilot contamination. It has two different effects. One of them is that it reduces the estimation quality, and the other thing, because we have extra interference during the pilot transmission. And the other thing is this, that the channel estimates become statistically dependent, despite the fact that the channels are independent to start with. And this correlation that we can observe here we have an inner product between the covariance matrices. That means that if the two covariance matrices from a base station to different users are small in some sense, for example, in the sense that the eigen values of the matrix we get when we multiply them together is zero, or they are really living in almost different subspaces, well, then the interference will be small. So this can really happen when you have different supports, or potentially when the other user is very far away, so that all of the elements in this other matrix are small. But pilot contamination will definitely make it harder for the base station to mitigate interference from this other user, because we don't have a clean estimate of the other user's channel. They are correlated with each other. And the first way of looking at this, that hopefully answers some of the questions that were asked, is shown by the following simulations. Here I am looking at two different users. One of them sends a signal to me as a base station array here, coming in from angle 30 degrees. Here is 30 degrees. Then the other user have an angle that vary between minus 180 and plus 180. And here I'm plotting this expression from the previous slide here that says something about how correlated are these estimates. It's a bit arbitrary that I selected that notion, but in a product premium scale with number of antennas. The interesting thing is that if I have one antenna at the base station, I get the same value all the time. So it doesn't matter from which direction the interfering user is, how correlated is my channel and that user's channel, they are the same. But when we start to get more antennas, 10 antennas, 100 antennas, we see that the interference between this user is large when the interfering user have the same angle as my user of interest, or when it has something that's like the mirror angle. From my array, if I get the signal coming in from 30 degrees or from minus 30 degrees, or in this case 180 minus 30 degrees, that is the same thing. It will get the same angle, let's say the same response vector at my array response. So this is one of the issues with having a uniform linear array. You should not use something that is that structure, because then you can get these mirror effects. But the important thing is that when they have the same angles, meaning that they have very similar covariance matrices, then the correlation between the channel estimates are large. And when they have very different angles, meaning that the covariance matrices are very different, lie in different subspaces, well then we have almost no correlation between them, even if the math says that we should have something. So that is one of the important things here, that the spatial correlation creates this behavior. In the ID Rayleigh fading case, you would always be in the same number here with the one antenna case. You will never see this behavior that users that have similar covariance matrices interfere a lot with each other in the estimation phase, and those with different ones have much less impact on each other. So some additional remarks. Pilot contamination exists because of the practical necessity of reusing pilot sequences between cells. And it's often described as one of the main characteristics of massive MIMO, but it's not unique to massive MIMO. This is something that you observe in any multi-user system where you need to reuse the same time frequency resources in different cells at the same time. But however, it might be that pilot contamination has a greater impact on massive MIMO systems because you have more users in the system, so it's harder to create large distances between users that use the same pilot sequence. And the eigenstructure of the channel covariance matrix determines the strength of the pilot contamination. And for example, one can try to assign pilots to the users somehow to make sure that users are in different angles, or more generally have very different covariance matrices. And how to do that is something that people are spending research time on doing. I will talk briefly about that later today as well. So the key point for channel estimation is that the uplink pilot sequences are very important. You have one orthogonal sequence per user in the cell, and I didn't talk that much about it, but you saw in all of these SNR expressions, the pilot length tau per u showed up. So because you have a long pilot sequence, you actually get the higher SNR as well. So if you would have an SNR of, say, 0 dB, and then you send a pilot sequence of length 10, then you actually have a 10 dB SNR in channel estimations. That's one of the positive things of sending sequences. I talked about MMSE estimation that use the channel statistics to obtain good estimates. There are other alternatives like the element-wise MMSE or the least square estimation. I'm not covering it here, but it's a way of simplifying things. Here we essentially only need to know the diagonal in the covariance matrices. Here we don't need to know anything at all about the covariance matrices. We are limited by the channel coherence. That makes it important for us to reuse pilots across cells. Intercell interference reduces the estimation quality, and the estimates becomes correlated, which is one way of looking at power contamination. The correlation is small for sufficiently different covariance matrices, but when you have different path loss or different spatial characteristics, it becomes small. And we will see soon that power contamination leads to coherent interference that is harder to mitigate. Before we take a break, let me just briefly start with the uplink, what we are doing when we receive data in the uplink. This was the kind of signal that we had before, where I selected a uplink combining vector, VJK, that I multiply with my received signal Y in order to try to decode the signal SJK that comes from my user of interest. And when I receive this thing, I have also a lot of interference plus noise. Interference from all other cells, or actually the same one, as long as I don't include my own user. And here I have in the product between channel and combining vector, channel from another user, and my combining vector. And here I have the signal from another user, and here I have noise. And when I'm now using my MSE estimator, the channel can be decomposed in the following way. The channel is the known part plus the unknown estimation error. That means I can take this expression here and I can replace h here with the estimate and say this is what I know, and then everything else here, including this term with the h tilde, the unknown, this is everything else, that's like interference and noise. And this is the information that I have in order to try to get what is the received, what is sent data signal on my user. And when I apply this kind of estimation, if we apply some known information theoretic results on how to compute the or compute a lower bound on the capacity for this particular user with something like that, what I really get is, you look here was my received signal of interest. If I take the absolute value square on that and take, what will that be? It will be something like this. Absolute value square of the inner product between my combining vector and my estimate of the channel, and the power of the signal S was PJK. And then the achievable performance now is what they call a spectral efficiency, is the expected value of a log 2 or 1 plus something that can be interpreted as an SINR that contains this in the numerator, and then it contains a lot of interference terms here. It contains the sum of all the cells and all of the other users except my own one, a similar term with my combining vector but their channel estimates, and here is the power that they are transmitting at. And here I have a sum of all the estimation error covariance matrices and the noise covariance matrices. And here I have my combining vector as well. This is a general expression for the uplink spectral efficiency for this kind of system. And the prelog factor here, tau e over tau c, comes from the fact that I'm only using some of the signals tau e of the samples that are tau c in general in the coherence interval for uplink data. Now we will finally take a break, and after that we will look into this thing, try to figure out. So I got a number of questions in the break, so I was planning to just briefly mention some of those things. One of them of the question I got was, what is channel hardening and what is favorable propagation? Because these two are actually two different concepts, even if they are kind of related. The channel hardening was the property that Eric was talking about, that a channel, when you take this norm of this channel vector and divide with number of antennas, this will look more and more like a constant value, even if it's a random channel from the start. So in Eric's case, this converges to the, or look very similar to beta value. In our case, it will look very similar to the trace of the covariance matrix divided with number of antennas, but it's the same kind of concept. Then the follow-up question is, do we get channel hardening with a correlated channel? Yes, usually you seem to get that, but it might harden more slowly because it is really the number of eigenvalues that you have that are strong and are at around the same value that provides you with the channel hardening effect. So in the examples that I had, when you have like 20 strong eigenvalues, the hardening will be as if you had an IID Rayleigh fading case with 20 antennas. So you might need many more antennas to really get a good hardening effect. The other question was, what is favorable propagation? That is something that usually means that two users' channel vectors are going to be more and more orthogonal to each other. And in IID Rayleigh fading, you get that all of the time when you have many antennas. In correlated fading, if the users have channels that are in exactly the same subspace, well then it will once again become, you need very many antennas in order for this to happen. You essentially need to have these 20 strong eigenvalues, that number needs to be a large number before the channels are actually starting to look at orthogonal. While if their users are in very different subspaces, well then you get this favorable propagation much faster. And that is something that we will see as important also when we go forward here. So before the break, we got this expression. When you use MMEC channel estimation, the uplink channel capacity of a user K in cell J can be lower bounded by this expression, which contained an expectation over different channel realization, different coherence blocks of a log 2 of 1 plus an SINR expression, which is a random quantity that changes with our channel estimates here in different coherence blocks. And this is something that applies for any choice of my combining vectors. And the question is, can we based on this somehow determine how we should select our combining vectors? Well, there is a result saying that the optimal thing is having the following structure. You should notice that what we have here is a matrix that is a sum of the covariance matrix of all the estimation errors and the noise here. And then here we have like VJK times the estimates of each of them. We have absolute value, so we can write that as the VHHV if you expand this expression. And that's essentially what they say here. We should select our combining vector in the following way. We take the estimate of the channel of interest, we multiply with the matrix with an inverse on, and this matrix is the sum of all the users in all cells, the power that they're transmitting on, and this is some kind of guess of what the true channel times itself is going to look like. The estimate times the estimate Hermitian plus the covariance matrix of the estimation error. We sum this up and then we add the noise here. This is what is maximizing that SINR expression. And if you put it back into the expression, you can simplify your SINR expression, and it's going to look in this form here. When you take an inverse of something that's essentially the same as here, except that from the first term here, I'm removing my own user's channel. And then when I take an inverse of this matrix, I multiply with h here from different sides. You don't need to read this exact detail and try to understand exactly what it contains. I will give you a nice example of what this actually means. We call this the multicell MMSE combining vector. What is the reason for that? The reason is that this choice is also minimizing what you can call the mean squared error in the combining part here. So say that you are interested in this signal here, SJK. If we subtract the received signal, y, times my combining vector, and we'll like the difference here in mean squared sense to be small, condition on the estimates that we know, then this is also what minimizes this thing here. So that's what we call the minimum mean squared error combining. Why do we call it the multicell minimum mean square error? Well, that's because the word minimum mean square error, or MMSE, combining was already used in the literature for single cell systems, and in that literature the MMSE changes when you change the setup, but it's easier to get the feeling that you have computed it once and then you change the setup, but you still call it MMSE, and that is what happened in literature. So therefore we had to invent this name, multicell MMSE. Had a question?
I was asking, is there a constraint on this VEIT?
Sorry, what?
Is there a constraint on these combining vectors?
No, there is no constraint at all on the combining vectors The interesting thing here, if you go back to this expression, is that V is showing up in all of the terms here. So you can scale V by a factor X, and then the same scaling will appear all the ways, and they will cancel out each other.
Because it is being done at the base station, that's why.
Yeah, exactly. So it's being done at the base station, and you are scaling the signal, interference, and noise with the same factors. So the actual scaling of the vector is unimportant here, but it's what's important is which direction it has, and this is giving us the right direction. And when in terms of the SINR, you can take any scaling factor in front of this and get the same result. But in terms of minimizing this mean squared error, it's only this thing here that does that. So this is what you really should use. Otherwise, in a real receiver, you need to do another step where you scale things.
Do we have to have all of the estimates available in all the cells to be able to do this?
Yes, and we will come back to that in a few moments. But let's first try to understand what does this really mean. So the MMC receiver consists of actually two different steps. The first thing is what you can view as a whitening of the signal. So say that we take the received signal, Yj, that is what we receive during the data transmission, and we compute a correlation matrix out of that one, or covariance matrix. Yj Hermitian, take expected value of that given our estimates. We call this Cyj. Then, if you take this thing and you multiply your received signal with the inverse of the square root of this thing, you have whitened your received signal. The received signal will now have an identity matrix as correlation matrix. So if you take the whitened here in the product and you do the math, you will see that this becomes an identity matrix. And the reason that I write this up here is that is actually what we are doing in our in the MMC receiver. So first, we are taking our received signal and whiten it like this. And then when we have whitened it, we select a combining vector. In the for the whitened ones, that is like a maximum ratio combining of the same way as Eric was describing before. What is the channel where we receive our desired signal is the original channel times the whitening factor that we get from here. So the resulting combining vector is this thing here, and then we need to undo the whitening procedure once again. So it is the estimate of our channel of interest times the inverse of this received covariance matrix. Received signals covariance matrix given our estimates. And this, it becomes even more clear if we look at a nice simulation example. In this example, I assume that there are two antennas and we have real valued signals. I can plot it like this. Then I receive a signal and I can select my combining vector as 2 dimensions and only real value, so it's only an angle that is important to us. And this angle I'm showing here, 0, 45, 90% degrees, and we move it around like this. And since my received signal typically contains different things, I can say that as I change my combining vector, the desired signal, which is like the estimate times my combining vector, absolute value squared, it will have this value here, to represent the black one here. This is a so-called polar plot, so the further from the origin we are, the stronger the signals are. So if we select this combining vector, which is maximum ratio combining, we will get the largest value of the desired signal. And then as I'm changing my angle, I will get smaller and smaller values until here, where I actually get 0 left on my desired signal. And then if I change the angle again, I can get the stronger signal again, then it looks like this. If I instead look at the interference plus noise part, if I select this angle, minus 30 degrees or something like that, you will get the largest path of the interference and noise, and then over here you get the smallest part, and then here on this, for this angle, you get a large value again, and then it walks around like that. And if you sum up the desired and interfering signals, you get the red part here. So you see in some directions, you get more total received signal, written like that. In some, you get less. And here, it is not really clear which direction should we put the signal in. Should we take something that points in the direction here where we get the larger signal? Should we take something that points in the direction where we get the least interference? Or should we take something in between, as the multicell MMC is doing? And how is it doing that? And what the complicating thing here is that this red shape here, the total received signal, is angle dependent. And if I whiten the signals, as I described, now it doesn't matter in which direction I put my combining vector in the whitened case, because I should always get the same received signal. I whiten it so the correlation matrix was an identity matrix. And since the total received signal power is signal plus interference, and now that sum is the same irrespective of which direction I look, well, then it must be that in the direction where the signal is at strongest, the interference now must be as its weakest. Otherwise, they cannot add up to the same value all the time. And that is what we see here as well. The black thing is once again the power desired signal in the whitened case. And now here I have the strongest signal. The blue one here is the power of the interference plus noise, and it has its smallest value here, where the desired signal is at the strongest, and it has its largest value in this angle directions, where my desired signal is at the strongest. Is at the weakest values when it's small, almost 0. And that means that in this case, it is very easy to select the best combining vector. This is multicell MMC. So that is what the multicell MMC is doing. It is whitening the received signal. It is then applying a maximum ratio combining filter, and then we have the MMC, the best solution.
How is this compared with the traditional MMC, where you only whiten the interference part?
So that would be essentially the same thing. It is. We can, if one play around with the matrix inversion lemma, you can see that you get the same kind of behaviors. It is the same combining vector. It is only a matter of how we illustrate it. In that case, it would look more complicated because you don't get that round circle, but it's the same thing.
Combining on the whitening and combining are done with regards to the interference plus not only interference, right?
Yes. So this part, this is the this CYJ is actually this matrix here. And in this one, going back to the question here I include all the users, including myself. So it's both the signal and interference. You can actually take out the term here that contains my own desired signal. That will change the vector scaling, but it will not change the direction of it. And one can show this with the matrix inversion lemma, that one can take out one of the terms that will only create the scaling of this vector. And there is this lemma for mathematics. If you have a matrix with columns x1 to xn like this, and you have a diagonal matrix d1 to dn, and you write x dx Hermitian, this is the same thing as taking the sum over the columns of x, one column times itself Hermitian times the diagonal element here. And the reason that I'm writing this up is that we got a lot of expression of this kind previously, where in those cases we had the power here of a user, and here we have an estimate of that user, and here we have another estimate of that. It had its own estimate of the channel, and then estimate of channel again here with the Hermitian on it. And in that way, we can write something in this form, and that is something that appears in this term here. This is a matrix. Instead of x, I call it h. This matrix contains the estimate from basis in J to all of the users in cell L. So user 1 up to user KL. I put them in columns and I put the matrix here. And then I put the same matrix over here, and then I have a diagonal matrix PL with all of the powers of these users. And this way we can write it in a compact form. We see also here that now it actually doesn't depend on which of the users that I'm transmitting to. It's the same expression in this inverse of the matrices. That means I can take the MMSE combining for user 1 up to user kj in my cell. The only thing that is different is that I was multiplying from the right here with my own channel estimate, and then I had put on the left hand side the power of that user, and I can put them together here as the columns in this form, and I can put the power here in the diagonal element. So this is one way of writing this multi-cell MMSE in a matrix form. So you just have to compute this inverse once and see that this is the expression that you get. Okay, so that is the optimal thing, but it's rarely used in literature. And one of the reasons for that is that you might have a high complexity because you have a matrix inverse that is proportional to the number of antennas, that is the dimension, and you need to estimate the channel to every user in the entire network from your base station. You can do that with the pilots that you have, but you still requires quite some effort in terms of signal processing or computations. And it's also difficult to analyze the performance mathematically, so I will show you some simulations on that. And it's also, I think that combining schemes that people have been developing for single cell scenarios have often heuristically been applied to multi-cell scenarios. That is my guess on the motivation why other schemes have been used. Of course, you cannot prove why people using the combining schemes that they have been doing. But I will talk now briefly about other schemes that are kind of simplifications on multi-cell MMSE that will achieve lower spectral efficiency but reduce complexity, let you estimate fewer channels, reduce the amount of required channel statistics, and they might also be more mathematically tractable. So this is the expression that we have for multi-cell MMSE. And say now that I can only afford to estimate the channels to the users within my own cell. So it's only the part in this first sum here where L and J are equal that I can compute. What should I do then? Well, then there is what is called a single cell MMSE, where I take away this sum here and I put the term where L and J are the same. So this is my estimate for my own users in the same way. What should I do with the remaining terms here for the other cells and all their users? Well, if I can't estimate their channel, I could replace their estimate plus estimation error with the actual covariance matrix of their channel instead. And this can be viewed as the MMSE combining in the case where I happen to only know the estimates of the channel within my cells. Then you will get something like this. This has been applied a number of times in literature. But one of the problems is that I still have an MJ dimensional matrix that I need to invert here. And if I would like to get rid of that, one thing I can do is to say, let's take away all the covariance matrices here. This estimation, I have good estimates. So let's take away this estimation error. Let's take away this covariance matrix from the users in other cells. They are probably far away. Let's skip them. Then we get only this term for my own signals, estimates, and the estimation noise here, or the noise part here. That is left, have this expression. And then if you play around with some matrix algebra, one can actually move around things in this expression. One can take what is put on the right-hand side here, move it to the left-hand side, switch the order of things here in the middle. This is a classical result. And now, all of a sudden, I have the channel on the other side. I have the inner products in the other direction. And that means that now this matrix here, which was before an identity matrix with size mj, now it is the inverse of this matrix with the powers of different users. So this is a kj dimensional matrix. So all of a sudden the thing I need to invert here is only kj dimensional. And this is something I call regularized zero forcing. then the reason that I call it regularized zero forcing is that if you take away this term here, this is zero forcing, and here I have regularized it. That means that you invert the matrix and you want to regularize something, you add a scale diagonal matrix to try to improve the smallest eigenvalues. Question?
What's the performance matrix that is minimized by this
this one?
Yes.
I don't know if there is any particular performance metric that
How did we choose it?
I chose this. So, I mean, this has been around the literature for many, many years. The regularized zero forcing, and I tried to just show here how you from the optimal thing can come to it. And I think where it comes from the beginning is that people have been saying that zero forcing is a good strategy, as Eric has talked about before, but sometimes it could be a bit unstable. And in those cases, you could regularize it and then it works better.
So this looks like the single set MIMO in the case you don't have.
Yeah, so actually, you're also right that if you have this single cell MMC, and all of these covariance matrices here are identities. So in the uncorrelated Rayleigh fading case, that will happen. Then you can sum everything up and say this is a scale identity matrix, and then it will look essentially like this. So that is also one way of defining regularized zero forcing. So in a way, single cell MMC and regularized zero forcing is more or less the same thing in the uncorrelated Rayleigh fading case.
Is there any scenario in which the single cell MMC, the second one will be equal to the third one? Maybe like, I don't know, maybe the HGG will be orthogonal to the two sums.
I think you can find such special cases, and I think in general, if you have uncorrelated fading, they will be very similar to each other. The next simplification now, since I call it regularized zero forcing, is to just take away this regularization term, and then you have the zero forcing as Eric have described it previously. This is called zero forcing because if I multiply with my channel matrix, the matrix with all of the users' channel from the left here as HJJ Hermitian, well then you will get a nice term here times its inverse, so it becomes an identity matrix. So in the case when you have, if you apply this thing, you will remove all the interference that comes between your users within the cell. And with the perfect CSI case, that is really removing all interference within your cell. In the case when you have estimated your channels, you only remove the interference that comes in along your estimated part of the channel. And then the last simplification would be to say, let's take away this matrix here. Then we get maximum ratio combining. What would be the reason to take away this matrix? Well, one motivation might be that the matrix here in the inverse is already a scaled identity matrix. That could happen when you have very many antennas, that the diagonal here becomes large because of channel hardening effects, and the off-diagonal elements are the kind of terms that appears in when you talk about favor propagation. They will become small, so then it will be almost identical. Another case would be if you start from regularized zero forcing and say I can take away this term over here because my noise is much stronger than the signals. Well, then I can also end up with something looking in this form. But this is the optimal thing, and this is in some way heuristic simplifications of it that will have lower complexity, be simpler to compute, but will also provide you with lower performance. And how low, we will look into now. In order to do that, I will define what I call the running example, which is set up with 16 cells. Each of them have a square size. They contain a certain number of users and the base station in the middle. And then I have a wraparound topology. So for a user in this cell here, 1, it might also appear here and create interference to cell number 16 here. I have M antennas per base station. I have K users that I deploy randomly within the cell. I generate these beta large-scale coefficients in the way that I talked about before. I select this parameter here that said what is the path loss at 1 kilometer distance as minus 148 dB. This is something I've taken from a 3GP model. I select the path loss exponents as 3.76, and the shadow fading have a standard deviation of 10. And actually, when you throw out users in this particular way, it could happen that the user in one cell, due to this random shadow fading, even if it's closer to one base station physically, it will get a better beta parameter from another base station. And I wanted to keep the cell notion as being a square here. So every time that happened, instead of moving that user to the other cell, I just regenerated the shadow fading realizations. That's just another way of getting this type of result. And this is some kind of macro diversity. You can say that if you are at a bad location, maybe another base station might serve you instead. But it's just simplification that I did. And I selected some values for the transmit powers, 20 dB per user, noise power minus 94 dBm. This was also dBm. dBm is, by the way, dB of milliwatt. So this is 100 milliwatt. And you have a bandwidth of 20 megahertz. The exact numbers here is not so important. The important thing is what kind of signal to noise ratio you're going to get. And for a user that are in the cell center, very close to the base station, I allow them to be 35 meters from the base station. You will get around 20 dB SNR. And when you are at the corner of the cell, you will get around minus 6 dB. And both of these numbers are before I add this random shadow fading, because with that one, you can get any number. And I will compare this Gaussian local scattering model with different values on the angular standard deviation with the uncorrelated Rayleigh fading model, so you can see some of the differences between these things. And how do we reuse the pilots between cells? I define a pilot reuse factor in a similar way as Eric did, where we can have these cases. Pilot reuse factor 1, that means that all the same pilots are used in all cells. That means that I need to 1 times k uplink pilots in total, so tau pu is equal to k. I can also say that every other cell here is using the same one. Blue one uses one, and this blue yellow one are using the other color. Then I need 2 times k pilot sequences, so more pilot sequences, but fewer cells are using the same ones. And here I have 4 different patterns, so then I need 4 times k uplink pilot sequences. How do we simulate the spectral efficiency in a system like this? Well, first, if you would like to create a simulation environment, you look at the macroscopic propagation effect. You drop the users randomly in your cell, then you compute the distances and angles to the base stations. Then you generate shadow fading realizations and compute the average path loss. Then you create your channel covariance matrix based on the model that you have using. And then when you have that one, you can also get the estimation error covariance from the expression that we had. Next case, you go to the microscopic propagation effects and generate randomly estimates of the different channels. And when you have those ones, you can compute some kind of instantaneous spectral efficiency. That's the same thing as we had before, but without the expectation. So you compute what you get for one particular channel realization. And then you take this expression and sum it up over all the users, and then you take the average over different channel realizations, and you can also take all different shadow fading realizations and user locations to get some kind of average sum per cell over the systems. This is how a simulation would work. Here is an expression or an example of what you get. So this is when you have 10 users in your cell, you have coherence blocks of 200 symbols, similar to what Eric had, and this is with universal pilot reuse. So we have a pilot reuse factor of 1. So you have k pilots. And we will look only on the uplink. And we get show the sum rate, sum spectral efficiency here, and here is the number of antennas. The top curve is with multi-cell MMSE, gives you the highest performance, and it increases with the number of antennas. Then we have the single cell MMSE, it gets also higher performance with number of antennas, but there is a small gap here. We have the regularized zero forcing, we have the zero forcing case, and then we have the maximum ratio case. So what we can see here is that for every approximation that we do, we lose something in performance, but we gain something in terms of complexity. And there are particular these different cases, the multicell MSC here at the top. We have like the regularized zero forcing that is slightly better than the zero forcing because it doesn't run into problems when you have few antennas. Zero forcing have problems when you have few antennas as compared to a number of users, because then it's difficult to invert that matrix. So you have the top curve, you have the middle curves, and you have the lowest curve with maximum ratio. And this is for the Gaussian local scattering model, by the way, with 10 degrees angular standard deviation. What happens now if we are adding some more pilot reuse factor? So let's remember this curve, point here, and we increase it to 2. We see that all the curves except the maximum ratio curve are moving up. In particular, the curve with the multicell MSC is going up. So when you have more pilots, in particular, you can estimate, you reduce interference towards the users in your own cell when you estimate the channels, but you can also get better estimate to the user in the neighboring cells. And that is what the multicell MSC scheme is using in order to remove the interference or reduce the interference from those users. For the other ones, the difference is much smaller. And if we go up to pilot reuse factor of 4, we can see that the term here for multicell MSC goes up slightly, but actually the curves here, they were going down again. But otherwise the same behavior. So if we just are summarizing this in the table, this is for the case when you have 100 antennas, 10 users. Then here is the pilot reuse factors. Here is the different schemes. And I have bold phases where we get the highest performance. So multicell MSC prefers a very large reuse factor. And the other 3 schemes here in the middle, that inverted matrices, but not as advanced as multicell MSC, they get around the same values. And they prefer a pilot reuse factor of 2. And then maximum ratio, which actually is not trying to reduce any interference in the entire network. It prefers a pilot reuse factor of 1. Because, yeah, if you increase the pilot reuse factor, you can get the better estimate to a user within the cells. But you will also consume more of your resources in order to do that. And that doesn't pay off because you have quite good estimates to use in the cell. It is the interference that limits you, nothing else. So from that, I would say that there are 3 schemes that are really useful in practice. It is multicell MSC because it gives you the highest spectral efficiency. But the downside is that it has the highest complexity. It is the maximum ratio that have the lowest spectral efficiency, but at least it has the lowest complexity as well. So if you cannot afford anything else, then use that one. And then, in between, I would pick the regularized zero forcing because it inverts much smaller matrices than single cell MSC, and it's more stable than zero forcing. That could run into problems when you have few antennas. So regularized zero forcing is some kind of good balance between these 2 different cases. So these are the 3 schemes that you should really care about from a practical perspective. Yes?
When you talk about the reuse factor and sequence length, and the sequence length will definitely reduce the coherence time because every antenna has to send more number of pilots. So that goes against the test for the shorter part sequence thing. And the reuse factor ultimately will also increase what we call the pilot contamination, is that correct?
So if you have a larger reuse factor, you move the users that use the same pilots as the users here further away. Over here, there are cells all around that interfere with you. Here is only the ones that are along the diagonal, and here they are even further away. So by using a higher pilot reuse factor, you will get less pilot contamination. But you will need to spend twice or 4 times the number of samples per coherence block to estimate the channels. And that reduces the number of samples you have available for data transmission. So you reduce the factor in front of the log, but you increase the SINR at the inside of the log. And there is some kind of balance when one of these effects is dominating. And for multi-cell MMC, it seems to always dominate to actually increase the SINR at the inside, even if you have to pay a lot for the reuse factor, for the spending more resources on the pilots. But for maximum ratio, you are fine with having short pilots and get more occasion to send data symbols per channel, per coherence block. Then, yes?
It looks in the figure that it is saturation. Is it true?
So we should not say so far if it saturates with number of antennas. We will look at that before we end today as well. But for any scheme here, even if you would, there will be no interference or anything like that. As you add more antennas, in the best case, the SINR will grow linearly with number of antennas. And then you put a log 2 on top of that. So in the best case, it will grow as logarithm of number of antennas. And this have this kind of shape so far.
So it's not saturating, it keeps growing.
It could do that. And the hint is that some curves here will saturate, some will not. But we'll come back to that. One can also compute other expressions using the kind of techniques that Eric was describing in order to get closed form expressions. I didn't intend to go into details on that. There is another bound called the use and then forget bound that here he's talking about in his book. And if you go with that one, you could compute a closed form expression for the SINR that you will achieve with maximum ratio combining. Eric presented some formulas for that, for maximum ratio and zero forcing in the uncorrelated case. In the correlated case, you can compute such formula using the same bound technique, but only for maximum ratio. This is the expression you're going to get, which looks much more daunting than what Eric was presenting, but it actually have a very simple implementation. So as I now have this formula part, it has a signal part, a non-coherent interference, a coherent interference, and a noise part here. Let's go through each of them. The signal part up here, it is proportional to the power that I'm spending, actually squared, because it also enters things in the estimation part. One should not overstate that because the power is also in this psi matrix here. But the important thing here is that I get a trace of a matrix, and this matrix contains the covariance matrix of the user and this psi that was an inverse of the covariance matrix that we receive of the received signal during pilot transmission. Then the exact formula there is not the important thing. The important thing is that take a trace of an MJ dimensional matrix. That means that we sum up the diagonal elements of an MJ matrix, and if nothing strange happens, that should be proportional to the number of elements that we're summing up. So this term will be proportional to the number of antennas. So that means that the signal part grows with the number of antennas, more antennas, higher signal. In the same respect, if you look at this interference term here that I call non-coherent interference, here is the sum of all users in all cells, and you have some term here contains one trace of covariance matrices divided with another trace of covariance matrices, and every time I take a trace of a matrix of dimension mj, I should get something proportional to mj. Proportional to mj divided by proportional to mj, well, this should be some constant. We don't know exactly what it is, but it should not grow with number of antennas. So that is why we call this non-coherent interference. Has some number, but does not increase with number of antennas. Then we have one additional term where we sum up the users that use the same pilot as my user, and I remove myself from that set. Remember, this was a set of users using the same pilot. And here, in the numerator, I have the trace of a matrix squared divided by a trace. So I get mj proportional mj squared divided by mj again. So this term should grow with the number of antennas. And this is then something that I call coherent interference. It grows with number of antennas, and yeah, it's visible from this sum here that it is something that has to do with pilot contamination. It has to do with the user that use the same pilot as me, so that their estimates, or the base station's estimate of those channels are correlated with the estimate of my own channel. And then we have a noise term there at the end. And what's important here is that somehow in this term that says something about the coherent interference, the covariance matrix on me, from my base station to my own user, and the covariance matrix from my base station to the other user is showing up here again. So if those two covariance matrices are very different, we could guess that this term should be small. And when they are very similar, they should somehow be larger. And let's look at that term. What happened with the coherent interference? In the same kind of setup as before, when we look at two users, we had one user at angle 30. This was my desired user. And then I varied from which angle my interfering user is. And here I show the size of this term from that user divided with the signal term here. So I see how large is the coherent interference with respect to my desired signal. If I have one antenna, it doesn't matter in which direction the interfering user is, because I will get the same amount of interference all the time. When I add more antennas, the interference depends a lot on which angle we are in. So when two users have the same angle, or we have this strange mirror angle as well for this type of arrays, the interference is larger. But it's not larger than in relative terms, it is never larger than it would have been in the single antenna case. And then we see that as the angle difference between them increases, the coherent interference also decreases. And when they are very different, like here, there is barely no interference between these two uses whatsoever. So here we see clearly what coherent interference has as what impact that has on our performance in the system. So it's mainly when users have similar covariance matrices that they will interfere a lot with each other. And what is also important here is to notice that this is what you get in the single antenna case, but also in a uncorrelated Rayleigh fading case. You will be here all the time, because it's only the path loss that is important, not the angular differences. So the coherent interference that you get here is never worse than in the IID Rayleigh fading case. It can only become better here because of you having different covariance matrices. And this starts to reveal something about what kind of correlation impact you will have. Will it be better or worse to have correlated fading? Here is a graph that tries to illustrate that. Here I look at the average sum spectral efficiency, and I'm changing now this angular standard deviation from 0, or actually very close to 0, up to say 50 degrees, which is a large area. And we looked at 10 degrees previously. And I look at the multicell MMSE, the regularized zero forcing, and the maximum ratio case. And these dotted lines here is actually what you're going to get with uncorrelated Rayleigh fading, so no correlation at all. 100 antennas, 10 users, and I think I chose a pilot reuse factor of 2 here. And what you see is that when you have a lot of correlation, it is clearly better to have a correlated fading than the uncorrelated fading case. Then after a while, it starts to go down and comes to something that is quite similar to the uncorrelated Rayleigh fading case. And in some of these cases, it becomes slightly worse. In some of the cases, it still keeps a little bit better. And actually, what is interesting with this uniformly linear array that I was looking at is that as you, since it's a uniform linear array, there are some directions where pointing away from the array where you can resolve uses much better than along the array. So for that reason, even if you put this one here in a case where you get multipath components from uniform distributed for all directions, as you start to get in these cases here, it's actually not seeing an IID Rayleigh fading case because the array have different resolvability in different directions. That is why they are not really converging to each other. One can also ask the question, okay, this is for some rate, what happens for particular users? And one can talk for a long time about that. On the average, as you move around in the world, you will actually, in these cases here, be with, say, 10 degrees angular standard deviation, you will always be better in a probabilistic sense. But it might be that you can find a location. I'm here, my users are at this particular locations. In this case, I will be better off with uncorrelated fading than with correlated fading. But if you are looking at many different snapshots, you will on the average, or in terms of a CDF curve as you move around in the world, you will be better off with correlation. One final graph here from the uplink, where what I've tried to do is to take the received signal with maximum ratio, with regular zero forcing and multicell MMC, and try to separate it in this different part. The signal part, the non-coherent interference, and the coherent interference. And for the case with maximum ratio, we have this nice separation in the formula, and here I'm numerically done the same thing for the other schemes. And I have plotted the powers. I divided with the noise power so that we get something in dB relative to the noise. So if we are down at 0 dB, well, something is actually equally strong as the noise. And I show you a result for different pilot reuse factors. And I have Gaussian local scattering, 10 degrees angular standard deviation, 100 antennas, 10 users. And if you look at something like maximum ratio, what we can see is that the desired signal is at the top here, and it maybe grows a little bit as you add higher pilot reuse factors because you get better estimates, but you barely see it in this decibel scale. However, the non-coherent interference, it is here and it's very large. So it's less than 10 dB smaller than the desired signal, and that has an impact on our performance. And down here we have the coherent interference, and we see that as we are increasing the pilot reuse factor, the coherent interference goes down because now there are fewer users that are actually creating pilot contamination. While the non-coherent interference is more or less the same all the time here. With regularized zero forcing, we sacrifice a little bit in desired signal. We cut down on the non-coherent interference a lot because now we are actually trying to reduce the interference between the users in their own cell. And zero forcing will do the same thing. The difference in coherent interference is almost negligible. With multicell MMC, we are further reducing the interference, non-coherent interference, and now we see that it actually goes down a lot as we increase the pilot reuse factor as well, because now we can use more and more good estimates to users in other cells to reduce interference as well. And you see that the coherent interference is also going down more here as well. So we can see that the useful signals are going down as we use more sophisticated combining schemes, but also non-coherent interference goes down and the coherent as well. So this is really the behaviors of these different combining schemes. So when it comes to the uplink here, we have a lower bound on the uplink capacity that was based on minimum mean square estimation, and this is an achievable spectral efficiency, meaning that is something that we can achieve in practice with Gaussian codebooks and things like that. And we maximized it using multicell MMC combining. There were also other choices of receive combining, and out of those ones it was regularized zero forcing maximum ratio that are the practically useful ones because they are looking into different balances between complexity and performance. Factors that affect the spectral efficiency is definitely the transmit power, but also the pilot reuse factor, the spatial correlation, and the pilot contamination. Insights that we get from the spectral efficiency analysis, and the running example is the following. that the received signal power and the coherent interference grows linearly with the number of antennas. Non-coherent interference and noise is independent of number of antennas, and coherent interference is actually negligible when you use large piled radius factors. Maybe I didn't say that explicitly, but that's what you can see here. For all of the schemes, this coherent interference is much smaller than the non-coherent interference, and this is in dB scale, so it's much smaller. Yes, and then I didn't talk so much about this additional bound, using them forget bound. Now I have a part on downlink spectral efficiency, but I was planning to actually skip over that one, and you will get the slides with all this material. But when you have done the uplink, it becomes a bit boring to do the downlink, because there is something called the uplink-downlink duality that says that the expressions that you get, if you compare an uplink expression for the spectral efficiency with a downlink expression, they will look very similar. It will just be that interference terms will have switched some indices. So in the uplink, the interference that comes in transmitted from users arriving at the base station, and in the downlink, the interference comes from base stations sent to users. So you have to switch some different indices and things like that, but essentially the analysis of things are very similar, and which non-coherent and coherent terms shows up at which users is also switching to some extent, but we still quantified the size of them, and that will still hold. So I think I will jump over that part. And jump instead to asymptotic analysis. So this is something that has been very popular to do in massive MIMO already from the start, with Marchetta's 2010 papers with an infinite number of antennas. So let's do that as well in the correlated case. And that really means that we look at what happens performance-wise when you add very many antennas. And one should not interpret this as something that I propose that we should put up an infinite number of antennas. This is more of an exercise of seeing what really is limiting us when you have a lot of antennas, and whether or not we can achieve any performance that you are asking for if we just add sufficiently many antennas. And of course, it's not physically possible to add more and more antennas. I mean, if you put them on a line, sooner or later you have reached around the whole globe, and then there is no more space for it. So it's not really a practical way of doing. And when we are doing this in a case with arbitrary spatial correlation, we need to impose some kind of conditions on what happens with our covariance matrices as we are adding more and more antennas. How do they scale? And if they are scale identity matrices, well, that is not a big issue. We just add more elements along the diagonal having the same value. But that is not the case that we're looking at here. And then we have two different conditions that looks a bit daunting because they're written in the mathematics, and mathematics often it's much more complicated to read and actually understand the impact of them. The first thing here says that if you take the trace of the covariance matrix, divide with the number of antennas, then the lim-inf of that is strictly greater than 0. What does that mean? It means that you sum up the eigenvalues, divide with the number of them, so the average value of the eigenvalues should remain strictly greater than 0. Practically, that means that as you add more antennas, you will gather more and more energy, and that energy will always be proportional to the number of antennas you have. If I put antennas here and then start to put them every 10 meters in that direction, sooner or later it will leave Gothenburg, and then of course those antennas will not contribute very much to the system. So that is not what we're doing. In those cases, it will not be satisfied. But if we put them on one array close together, adding more antennas should gather more energy. The second condition is that the spectral norm, which is the largest eigenvalue of the matrix, the largest value it will gonna take when we add more and more antennas would always be smaller than infinity. So that means that that this more and more energy that we are gathering from our array will not be just focused in one or a few directions. the number of eigenvalues that are large that we showed before, those were 30 out of 100. If I add more antennas, they will still be, say, 30% of all the elements. It will be a fraction of them perhaps that are large and not a fixed number. In those cases, this satisfies. So first condition, expected channel gain grows with number of antennas. Second condition, no eigenvalue grows without bound. And actually one can show that these two conditions are sufficient to get this channel hardening effect, that the norm of the vector squared divided with number of antennas goes towards a constant value. Under this condition you can show that that happens by looking at the variance.
What's the necessary condition?
I write this as a sufficient condition because if you want to show that the variance of your squared norm divided with number of antennas goes to 0, then these two assumptions will be helpful for you. But maybe you can find some other clever case where that is not the case, where you don't need these conditions but you still get channel hardening. So I don't know what is a necessary condition, but these are sufficient conditions. I also define the notion of linearly independent covariance matrices. And you probably have heard about linear independence before. Something is linear independent when you can't write it as a linear combination of the other ones. So in here we say that a covariance matrix R is linearly independent of some other covariance matrices if we can't write R as a linear combination of R1 to Rn here. And mathematical, that means that R minus a sum of the other covariance matrices multiplied with some scalars will be strictly greater than 0 for whatever values of these scalars that we are selecting. So for all such values. And I also define asymptotically linearly independent. That means that more or less the same thing, but now I divide with number of antennas and I look at what happens with this expression when you have very many antennas in it. And these two things are actually not really the same. You can have something where this R here is different from the sum of the other ones in only one element. Then they will be linearly independent, but they will not be asymptotically linearly independent, because if I divide with number of antennas, that one element where they're different will be divided by m, and then that will go towards 0. So this is a stricter condition where I need them to be different in a larger way. And here is an example of that. Look at the two covariance matrices, R and R1. The first one, both of them are diagonal for simplicity here. One of them contains 2 times identity matrix and then an identity matrix. And the other one is just pure identity matrix. And the first part here is m prime, and the other one is m minus m prime. So both matrices are m by m. And m prime is so far just an integer number, a constant. Then if we compute this difference between R and R1, multiply with some scalar C1, you can expand and compute exactly what it becomes for this particular case. And you can show that this expression becomes smallest by taking the derivative if you put C1 equal to this expression here. And the exact values here are not so important, but that this is smaller or equal to this expression. M minus m prime times m prime divided by m squared. If m prime is a constant, then it says, and this is proportional to 1 over m, so you have m divided by m squared. So in that case, this will go down towards 0 as you add more and more antennas into it. So in that case, we are not asymptotically linearly independent. They are different between each other, but the part, the way they are different, is only a small m prime sized part of the matrix. However, if I say that m prime is now proportional to m up to some factor, maybe 20% of the eigenvalues are different. In that case, here I get something that's proportional to m divided by proportional to m squared. So then we have something that is constant, and you can work out here, you get 1 minus a times a That's what it's going to become. And in that case, this is not depending on M anymore. And now we get something that is linearly independent. So we can see here, subspace where the matrices are linearly independent must have a dimension that is proportional to the number of antennas. That is what it really means. And they can still be diagonal matrices like this. And here is one important example, I think, where I compare two different diagonal elements, diagonal covariance matrices. One is an identity matrix, and one is a scaled identity matrix, or no, it's a diagonal matrix with different elements here. What I put on the diagonal here are IID, positive random variables. I put just something random into that matrix, and then I put something else here that's a deterministic value. So this is one way of generating the covariance matrix, and here's another way. Then if I look at this condition of asymptotic linear independence, and I start to rewrite things, well, I get one of the elements here minus C1 times 1 from this matrix, and then take the absolute value square of that, sum it up for all the antennas, and divide with the number of them. And then by what is called the law of large numbers, one can show that this converges when you have many antennas to the expected value of the difference between one of these elements minus C1. And it could be any of the elements because they have the same distribution. And if you should pick C1 to make this as small as possible, well, what you should pick is C1 being equal to the mean value of epsilon. Then you get this expression over here. And this is actually the variance of each of these elements. Meaning that if you just create one of the matrix randomly, somehow, any distribution, as long as the variance is strictly greater than 0, which any random, truly random variable will have, you will get something here that is equal to the variance, and it will be strictly positive. Meaning that I would say that if you could take any linearly dependent matrices and then you add some small variation like this randomly, then you can use this type of proof to show that it will be asymptotically linearly independent. So someone said, but I know two covariance matrices that are linearly dependent. Here are them. And then I will say, yeah, sure, but add a small random variations to the other one, and now you have something that is linearly independent. So any case where something is linearly dependent is unstable. And therefore we can expect it will never happen in practice that you have something that's exactly linearly, asymptotically linearly independent. Or linearly dependent. Everything will be practical covariance matrices are asymptotically linearly independent. And that is the takeaway message, which will be very important when we now look at the asymptotics. The first asymptotic is a bit classical. What happens under this assumption 1, which was what happens when we scale the covariance matrices to two conditions, if we use maximum ratio combining using this closed form expression that we have, then you can show that the difference between that expression and the following expression goes to 0 as we add more and more antennas. And this expression is more or less an expression where I've taken away the noise term, taken away the non-coherent interference. I only kept the signal part and the coherent interference here, the pile contamination terms. So this shows that the impact of noise and non-coherent interference vanishes while the coherent signal and the coherent interference terms remain, and therefore in most cases this will become a upper spectral sufficient limit. As you add more and more antennas, you converge towards a limit that is determined by the covariance matrices of the users, how they are generated. So you need to put in larger matrices here to determine what it becomes. In the IID Rayleigh fading case, you can put in these scale identities here and get these values in closed form directly.
The perturbations we add in order to make the covariance matrices linearly independent. Practically, how can we do this for just one impact?
No, yeah. So you're never going to do that yourself. I'm just saying that you will never be able to measure. users with linearly dependent covariance matrices. It doesn't exist in practice. It only exists in very extreme special cases where someone have created that scenario. Because if you at this small location would get this linearly dependent covariance matrix with someone sitting here in the audience, then if I just move a small bit, that will be like getting some kind of perturbation, some small variations in the covariance matrix, and that will be enough to break the linear dependence. So that is a very extreme thing. It will never happen. So I'm not saying you should create the perturbation. The reality will do that for us. You can derive a similar type of things for the downlink expression that I didn't show you. With maximum ratio, at least the takeaway message is that there is an upper limit on the spectral efficiency as you add more antennas into the system. If the base station is instead using this multi-cell MMC combining, using these MMC channel estimates that we have, then the uplink spectral efficiency of user K in cell J grows without bound as we add more antennas to the system. The totally opposite result, no limit. And this holds under this assumption 1 and under the requirement that the covariance matrix of my own user from my base station is asymptotically linearly independent of the set of covariance matrices of the other users that use the same pilot as me. So you get rid of pilot contamination, or not pilot contamination, you get rid of the coherent interference. It doesn't limit you if the covariance matrices are asymptotically linearly independent. And that is something that always happens in practice. And the reason for this is the following. If your covariance matrices are asymptotically linearly independent, well then if you take one estimate minus a constant times the other estimate, you can write it in this form. This part was the same, we looked at before, the received pilot signal multiplied with your pilot signal. Here was the same psi, and then you have different covariance matrices here and different scaling factors. And if these are linearly independent, well then these estimates will be that as well. So even if they are correlated with each other, they are pointing in different directions, and therefore you can't write one of them as a linear combination of the other one or scaled version of the other one. Similar things can be proved in downlink, and here is a description of that. Say that this plane here is the subspace spanned of all of the other users that use the same pilot as me, their channel estimates. So for my base station, I just gather those channel estimates. I see here is the space where that they are spanning. And then the estimate of my channel is pointing slightly in a different direction. It's not exactly in that plane due to the asymptotic linear independence of the covariance matrices. And that means that I can pick a combining vector that is orthogonal to this subspace that is scale spanned by the users that are interfering with me in the pilot transmission. And by doing that, I will get no interference, no coherent interference from them. And this vector will still be not orthogonal to my own channel. So that means that I can make sure that all of the interference terms are 0, while my desired signal term is non-zero. And this I can only do if they are linearly independent covariance matrices. Otherwise, this channel will also lie in this subspace. A simple example where I try to take this to the extreme. I have two base stations at different locations. And I put out two users in each cell. They have only a 3.6 degree difference. They have almost the same covariance matrices, but not exactly the same. Here I have user 1 in one cell. Here I have user 2 in the other cell. User 1 in cell 1, user 1 in cell 2, they are at slightly different angles. User 2 in cell 2, user 2 in cell 1. And I have two users. I have pilot sequence length of 2. I have minus 2 dB SNR for my serving base station and almost the same SNR from the interfering base station. And I once again use this Gaussian local scattering model. But I neglected shadow fading just so I don't need to impose any additional variations on this setup because it's difficult enough to simulate. Here is what happens. I have the average sum spectral efficiency in my cell with respect to a number of antennas. And note here that I put logarithmic scales. I have 10, 100, 1,000 antennas. And what you can see here is with maximum ratio, zero forcing, regularized zero forcing, single cell NMC, all of them seems to converge to a limit, while the multi-cell NMC case goes up towards infinity. And it starts to grow linearly here, and linear in log scale means that it grows with log of number of antennas, as we mentioned earlier. Then at practical number of antennas, you might still be always here in practice, so maybe this is unimportant from practical purposes, but from an asymptotic perspective, this is really what happens. So asymptotic behaviors, key points here is that the impact of noise and non-coherent interference always vanish, irrespective of which method you're using. They also vanish with maximum ratio. The coherent interference caused by pilot contamination can be a challenge, and it only vanishes if you use this multi-cell MSC scheme. In that case, the spectral efficiency grows proportional to the number of antennas. And spatial channel correlation is very important here. It enables this unbounded spectral efficiency when using multi-cell MSC, and it determines the upper limit that you will get with the other schemes. And knowing, of course, the channel covariance matrices is then very important. However, in our recent work that I'm referring to here, we show that you actually only need to know the diagonal of the covariance matrix, as we talked about earlier as well, in order to get something like this. So you can do some variations on these schemes. And how do we, in general, estimate covariance matrices? Well, we use the pilots. The pilots that we have, we can use them to form a sample covariance matrix and get an approximation of covariance matrices from that one. But that's not the topic of today. Any questions at that point? Then I will briefly talk about spatial resource allocation before we end for today. So what does that mean? Well, we actually in practice have, say, thousands of users residing in one particular cell. But it's only a few of them that is actually active at the given point in time. And there's also be a varying number of users per cell. So how does this these two facts affect what we do in our systems? Well, we know that we have multiple users that are sharing the same time frequency resources, and that the pilot sequences are key to separate the users. And we cannot assign these pilot sequences once and for all to a user, because most of the time the user is not active. So we should only give it to the users when they're active. And then we have this assignment problem of who should get it and when. So there are three important subtopics here that I will briefly mention. One of them is the pilot assignment. One of them is, should we always schedule all users and separate them spatially by pre-kernel combining, or could it sometimes be good to separate users in time and frequency? And how does the traffic load variations in terms of having varying number of users affecting the system? So the first thing was the pilot assignment, and we have looked at this in a simple way where we had pilot reuse factors. So there are mainly two different approaches that you can find in literature. One of them is to try to allocate sequences directly towards the users. And that is a combinatorial problem. You should take all of your pilot sequences and give them out to the user, try to find the best way of doing that. And that is totally crazy to try to do that over a large system in an optimal fashion. So therefore you can find people in literature that try to do that in a greedy manner, for example. And the other option is to do this pilot reuse factor, where you take your tau PU pilots, divide them into F groups, and then you have tau PU divided by F pilots in each group. And here is then in a non-regular setup how you could potentially create the different groups. And the second approach is definitely the simplest one, because then you can offline, when you create or deploy your base station, you have to select which base stations that should use which of these different patterns. So each of these areas is one cell. But you can, on top of that, always apply some kind of greedy allocation as well. These are not two different competing methods. What I think is important is the following. In this case, I have been looking at a case with 100 antennas, 10 users, the same Gaussian local scattering model as before, and I have taken the same setup and I have given different assignments of the pilots to the users. So I let the users stay still and I randomize the pilots' allocations, and I do this thousands of times so I can plot some kind of cumulative distribution function of the sum spectral efficiency that you're going to see per cell. And the black curves is with pilot reuse factor of 1, and the blue curves is with pilot reuse factor of 2, and I'm using once again these square cells in the running example. And what you can see is that there is barely no variations with maximum ratio and regular zero forcing. Maybe some variation with multicell MSC, but they are almost flat. So the conclusion of that is that in terms of a sum spectral efficiency perspective, it doesn't really matter who you give the pilots to. The sum spectral efficiency is almost the same. You can gain a few percent in performance, but that's it. However, if we not zoom in at one cell and look at the users that are the furthest away from the base station, and then we look at what happens to its performance as we are changing the pilot assignments. Here is the CDF of the spectral efficiency of the weakest user. And we see that that one is varying much more. We have maximum ratio, regular zero forcing, multicell MSC. We have the two different pilot reuse factors. And it's not even a smooth curve here. There's happening something strange here around 0.1. Why is that? Well, probably it's like there is one other user in the system that is interfering with you a lot if you happen to get the same pilot as that guy. And with 10% probability, you will get that if you give something at random. So as long as you stay away from that, you are happy. So from the weakest user perspective, it is important how you allocate your pilots. From a sum perspective, it's not so important. And this is something that you seldom see in the literature because people that have been looking into pilot assignments have focused on the worst users. The other thing I wanted to talk briefly about is about scheduling. And I would claim that it's like this. Here I showed the sum spectral efficiency, and here I showed the number of users that I'm serving, or actually, Eric promised that I was going to say something about multi-antenna terminals. So let's do that. Say that you have a user with multiple antennas. One of the things you can use those antennas to is to send multiple streams to them. So instead of having 10 users getting one data stream each, you can have 5 users getting 2 data streams to 2 different antennas or to this user. So here I'm actually having the number of data streams that I'm sending. And then I'm claiming that it's going to be like this. As I add more users or data streams into the system, the sum spectral efficiency will grow up to a certain point where it has its maximum value, and then it will go down again. And based on that claim, I will define 3 different operating regimes. One of them is the multiplexing regime, where the sum spectral efficiency is almost growing linearly with the number of users or data streams. So that means that I add more users into the system, they get almost the same spectral efficiency as the existing users are, so therefore it grows. But after a while, I'm coming into a saturation regime where, okay, I'm adding more users into the system, but I have now so much interference in the system between the users that as I'm adding more users, I will reduce the interference on everyone, and I will not increase the spectral efficiency cake. I will just divide it between the users. So I can still add more users into the system, and we get the same sum spectral efficiency, but less per user. And then eventually, I add so many users into the system that the sum spectral efficiency starts to go down. I call this the scheduling regime because you never want to be there. If you have so many users that you ask for being over here, well then you should operate here, around here instead, and let users take turn on accessing the system. So these are the 3 different schemes. Let me show what happens if we look at, for example, a downlink with this model that we had before. 100 antennas, varying number of users, 200 as the coherent block length, same model as before, and we see this type of behaviors. As you add more antennas, the sound spectral efficiency first goes up, then it reaches a maximum with regularized zero forcing and maximum ratio is here around 40. With multicell MSE it is 50, and then it starts to go down again. So it seems to be 40, 50 somewhere there. More users than that you should not schedule. And in this case we see that you have 100 antennas, so it seems like you should at least have twice the number of antennas and users. And some people, maybe myself, have written in papers, a massive MIMO system is a system where you have an order of magnitude more antennas and users. This is showing that you don't really want to operate in such a case. You should perhaps say it's a system with twice the number of antennas or more than the number of users. Because from a sound spectral efficiency perspective, it's better to just load the system a lot until you reach this point. Third thing I wanted to mention was what happens if you are varying the number of users in your cells. And one way of doing that is to say that instead of having k users all the time, I put k into a random number generator, and that will give me how many users I have for the moment. And a classical way of doing that is to put it into a Poisson random number generator. And if I put the Poisson number with k as parameter, I get the mean value of k, but I get a random number of integer users. And here I have 10 users, then it looks like this, 20 users, then I have this distribution. So this is the probability and number of active users. And then I have actually cut off here, I say I'm not allowed to have more than 40 users. So in the case I have 40 users on average, I will most of the time have more, and then I limit things here. But you can see that as you have more users, not only that the mean is increasing, also the standard deviation is increasing with the number of antennas. So what happens now if I would look at what happened on the sum spectral efficiency for a case like this? And this is what happens. I'm comparing the sum spectral efficiency versus the number of users here with having exactly k users, or on average k users, and then I generate the number of users with the Poisson random number. And I say that if I get more than 40 users, I have only 40 users, no more. And the blue curve is exactly, the dashed one is on average. And they are more or less the same. For multicell MSE, regularized zero forcing maximum ratio, more or less the same. So we can, and these are random numbers different in different cells. So that means that we can interpret all of this result with a given number of users per cell as the sum spectral efficiency we get within this number on average. And the reason for that is just because things are growing kind of linearly. So half of the time you have less, half of the time you have more, and on average, since it grows almost linearly, you get the average number that is more or less the same. Over here you lose a little bit because half of the time you are more than 40, and I didn't allow for that. So that is where when you're saturated you can lose something. So pilot sequences are key to separate users spatially. Some spectral efficiency is little affected by the pilot assignment, but the individual users can be greatly affected. So that is very important to keep in mind when you assign pilots. In terms of scheduling, all users use the same time frequency resources whenever needed is one claim. However, when you have a very large number of users so that you have reached the top sum spectral efficiency value, then you should start to do time frequency scheduling and let some of the users take turns. And in terms of traffic load variations, it's easy to simulate average performance under traffic variations because on average k or always exactly k brings you almost the same results. I had one part about power allocation as well, and I think I should jump over most of these parts. What it's really about is that we somehow should select the powers. So far I've actually have equal power allocation for everyone, and as Eric was pointing out, that might not be a good choice if you want to maximize something like the worst user's performance in the system. And this is not an easy problem because you have KL and the sum of the cells, number of users in the entire system, and you have a spectral efficiency in the uplink and downlink for all of them, and you should select your combining and precoding vectors and your transmit powers in both uplink and downlink to somehow try to optimize something like this. And that is not very easy to do. So what one can do is to try to, if you look at, for example, the expression that I didn't show you what the expression looked like in a downlink, but it has this form in general, a factor of how many samples per coherence block that you use for downlink data, log 2 or 1 plus your downlink power, some factor that depends on your channel and your precoders, a sum over all the interfering users, some power here, some value that depends on who you are, if you're interfering with different users, so their precoding vectors and things like that, some noise power here. And giving something like this, one can define a utility function where we somehow try to maximize the performance. One choice would be the max sum spectral efficiency, so the sum of the spectral efficiency for all the users. One would be the minimum of all the spectral efficiency, that's some kind of network-wide spectral efficiency, maximum fairness. And the thing that Eric was describing calling maximum fairness is not network-wide, is something more heuristic where you try to make sure that to maximize the lowest one within each cell, but then balance somehow between the cells with the particular heuristic algorithms that you find in this book. And another option is to maximize the product of the SINR, which is essentially a high SINR approximation of the max sum spectral efficiency. And if you formulate a power optimization problem in terms of maximize this utility function, one of these three different choices that I was describing, by selecting your downlink power location with respect to some power constraint, saying that for each base station I have a maximum power that I can use, and I sum up that powers between for my different uses, then I have an optimization problem. And if you're familiar with optimization problems, you know how to look into these if they have a particular structure that is well known or not. And for these different cases that I mentioned, the maximum sum spectral efficiency, it is known that this is a non-convex program that's very hard to solve in general. For the maximum fairness case, it's a quasi-linear program. It's relatively easy to solve. With the max product SNR, it's a so-called geometric program, which is also relatively easy to solve. And that is what we have done. And I will just show you, to wrap up here, a case study where we looked at a similar setup as before, but now we use a 3D-PP, 3D model for non-line of sight cases in urban microcell system. So this is based on the Quadriga implementation that anyone can use. We optimized the power allocation as I mentioned. We used least square channel estimation. I haven't talked about that, but I wanted to do this without assuming any channel statistics, just to show what you can achieve in performance. I used maximum ratio or regularized zero forcing processing. I put a cylindrical array with 100 or 200 antennas. And if I have 100 antennas, I can either have 10 antennas around and 5 different levels and 2 different polarizations. So on each antenna, I've cross-polarized them. Or I can have 20 antennas around, 5 vertically, and only 1 polarization. And in the case where I have 200 antennas, I look at the same 20 around, 5 vertically, and 2 polarizations. I assume that the base station is 25 meters above the ground. The users have a height of 1.5 meters. And the reason to look into these 3 different cases is that in the second case, you have the same number of RF chains. So then you can look at, would you like to have a larger or smaller array? Would you like to have polarization or not? And in the 2 cases here, you have the same physical size. It's the physical size and not the hardware that's limiting you. Have some assumptions. You can look into exactly how those are working, but it's quite enough similar to what we had before. Now we're dropping users randomly and associated with the base station that gives you the best path loss. And if you optimize the max product SINR, this is what you're going to get as a cumulative distribution function for the downlink throughput. It varies between different users in the cells when you maximize the max product SINR. And we can see if we compare the different types of arrays here. The more antennas we have, the more happy we are, as we would expect. And if we are limited to having only 100 antennas, then it is better to have a large array with only one polarization, or you can switch polarization between antennas, doesn't matter, than having a smaller array with two polarizations at the same locations, because it is the bigger aperture that helps you to see more things. And you can see regularized zero forcing performs better than maximum ratio. If you apply maximum fairness network-wide, you get more of the same values for everyone. If you look at some kind of graph here of the performance for different users, the 95% likely performance that 95% of the user will get is higher when you use maximum fairness than if you use product SINR. Well, if you maximize the max product SINR, you're going to get much higher performance for the stronger users. Here you can get twice or 3 times the performance for the best users in the system. So it depends on if you would like to help the weakest or the strongest users, or get some kind of balance between these things. And I skip over the uplink part here as well. So to summarize, in this case study, we looked at a 20 megahertz channel. I didn't say that. The downlink performance that we get per cell is 485 megabit per second over all my users. So it's like 10 users that are separating that. That gives you some kind of area throughput with certain numbers. The uplink have a 252 megabit per second. And I have another value for the area throughput. The reason for this 2 times difference here is just because I allocated 2/3 of the data symbols for a downlink and 1/3 for the uplink. And one can see clearly that there's a trade-off between high average throughput, which gives you this number, and user fairness in the system. If you compare that with an LTE system, it will in a similar system get these numbers in area throughput in megabits, and here we have gigabits. So it's like a 30-35% higher throughput that we get in these cases. And the gain comes from the coherent pre-coding and combining that gives you better performance per user, and from multiplexing many users in the system. So I'm reaching the end, and before we wrap up, I just want to briefly go through some open problems in this topic area. And you can definitely have a look on the slides when I send them out later today, and come and talk to me later during the school as well about these things. One of the things that's very important is to make massive MIMO work in FTD mode. We're going to hear more about that tomorrow. This has been a long-standing problem. People have been hoping to do this efficiently already in the 90s. Channel measurements, modeling of channels, data traffic modeling, a lot of different things that need to be modeled in an appropriate way for a future massive MIMO system in order to really be sure that we are measuring performance in a way that is realistic. A lot of implementation-aware algorithmic design that is important. For example, to implement zero forcing or regularized zero forcing or these multi-cell MMC things with the complexity that is more like maximum ratio. And to try to get a maybe lower resolution, energy efficient hardware into it. Maybe we can cut down on the hardware components and do some clever approximations in order to get good performance in an energy efficient way. Cross-layer system design is also important. We have focused a lot on the physical layer and the signal processing here, but there are also protocols for random access, for system information broadcasts that are very important to make a system work. I touched briefly on the spatial resource allocation and on the power control, where it's important to balance between some performance and fairness between the users. Estimation of the spatial properties, particularly on the mobility, was something that people asked about, and that's definitely an open problem. And in terms of information theory, if you're into that, finding tighter bounds on the capacities, for example, without relying on channel hardening, could be very important and interesting. And to find some kind of non-trivial upper bound. You can always neglect a lot of things and get a huge value for an upper bound, but something that says as a reasonable upper bound on the performance as well would be of interest. New deployment characteristics like having multiple antenna users, which we definitely will have in practice. You already have 2 receive antennas in your phone, so there is no reason not to use those ones in the real system. distributed arrays, in the extreme case something called cell-free massive MIMO, when you distribute a lot of antennas over a huge area and essentially don't have any cells anymore. And you can try to think about if you can exploit having large antennas in a new and clever way. We have seen that we can do it to cut away downlink pilots, for example. Maybe we can enable simpler hardware and algorithms and something else that we haven't thought about yet. And finally, the ground question for later on is, what will be the successor of massive MIMO? Suppose that we in 5 years' time or 10 years' time have a massive MIMO system that performs as well as theory says. How can we move forward from that? How can we get another 10 times performance boost? That's an interesting thing to look into, if someone have an idea about that. So that was everything for today. Thank you.